Testing on YouTube. 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 Come on. YouTube, YouTube, YouTube. All right. That seems like it's working. And we should be live on X shortly. How's it going, Cigar? I think we're probably live on X now. Let me just double check here. All right, let's check, make sure. Why is it not live? Come on. Loading. Click. 8:30 a.m. Should be live. Ah, there we go. Let's double check that. How's it going, Oma? I like AI and Ed. We're going to start here shortly. Just double check and make sure everything's working. All right. We are good to go. How's it going, Zorg? Yeah, sorry about no streams last week. I was actually in the Bay Area for a work visit, so I was doing some stuff, but we're back. Let me move this because I can barely see what you guys are saying. All right. In the era of closed AI, Karpamambathy doing good work, giving us a glimpse of cutting-edge technology. Yes. All right. So let me actually blow this horn, and then we'll get started. All right. Welcome, everybody, to another Hoopo's stream. This stream is going to be a little bit different than what we've been doing. I feel like we've been doing some paper streams for quite some time now, but we're going to try to go back to some coding streams. So this weekend we're going to do kind of a two-part series coding stream, and we'll see how it goes. See if people enjoy it. If not, whatever. What I figured we could do is this stream, I called it something weird. It's called Karpamambathy, and really, it's inspired by the latest Karpamambathy video. So if we actually go YouTube Karpamambathy, he has a really good YouTube channel, highly recommended, and he released this video here, where he basically writes GPT-2 and goes through all the different parts, and eventually ends up training it on his setup. It's a very good video, highly recommend it, but I was like, okay, why don't we just kind of expand on some of that? And you can actually go here. This is the repo that he's using. This one right here, build nano GPT. Just one, basically just one file here, train GPT2.py. And I figured, why don't we combine this with this? So this is the State Space's Mamba. It's a very popular repo. You can see over 11,000 stars here. And this is a repo that implements the state space model known as Mamba, more colloquially. And they recently released the Mamba 2. So for quite some time, all the Mambas were using this one, Mamba, but now we have a Mamba 2. So yeah, I'm going to basically try to combine Karpamambathy's training code here, which is really just for a GPT-2 decoder-only transformer, which is just a bunch of self-attention transformer blocks stacked on top of each other. And I'm going to see if I can put in some Mamba blocks. And the reason I'm going to do that is because if you look at a lot of these Mamba papers that are coming out recently, you got here an empirical study of Mamba-based language models. A lot of them are starting to do this trick here. They're starting to do these hybrid architectures. So you have a hybrid architecture consisting of 43% Mamba 2 and 50% basically attention. The MLP is part of the attention. So I was like, okay, well, what if we took GPT-2 that Karpamambathy made and replace some of the blocks with Mamba blocks? Maybe we get something cool, right? I also just wanted to spend some time in this repo, right? This is a training script written by one of the best ML engineers in the world, who's Karpamambathy. So just like spending some time inside this code, you know, like his particular style of doing things, his, you know, maybe some of it rubs off. So the goal here is going to be to replace some of this. So actually, let's get to the actual, this is the data loader right here, GPT. So you see how the GPT module here is really just a bunch of these blocks, right? And those blocks are really just layer norm, self-attention, layer norm, MLP, which is basically the standard kind of transformer block. So we're going to try to replace some of these blocks here with some Mamba blocks, Mamba 2 blocks specifically, to try to create a kind of a hybrid architecture. So this is not going to be state-of-the-art at anything, right? GPT, this GPT is an older GPT. I don't have a big cluster to train this on, so we're really not trying to push any kind of state-of-the-art performance boundary here. You know, this is really just more about getting the reps in, right? A little coding project where I just kind of do a little something, you know, come out with some cool streams. And really the point of this is just to learn a little bit, get more familiar, maybe make this a little bit more entertaining for you guys. But I'm not under any delusion that I'm somehow going to create the next architecture that people will be using, right? If we get to that point and we get that working and that seems to be doing good, then what I kind of want to try is I want to try this. So another interesting task that has kind of come out, it's been around for a while. This paper's a little bit older if you notice that, but there's a recent update to this. This is the ARC challenge. Yeah, so the abstract reasoning corpus. So this is like the creator of Keras, this guy Cholet. He's basically like a mini Yann LeCun, right? Similar kind of guy. Like he's got the French accent. He's got the kind of spicy contrarian takes, but he has his own secret evaluation benchmark, which he calls ARC, which is like these weird kind of like almost like these IQ puzzles where like you see some kind of pattern and then you have to predict the next pattern. And he hand designed all of these. And they're basically intended to, in his words, differentiate between a model that has a general intelligence and a model that's just kind of copy pasting, in his words, right? Like, I think that these LLMs already have a type of general intelligence, so I kind of disagree with him that they're stupid, but I figured this would be a kind of a cute little task that we could kind of easily try, right? And there's now a $1 million prize for this or something crazy like that. So yeah, we'll see what happens. You can see the original commit is 5 years ago, which is when the original paper came out, but he has made updates to this, and I think now it's the $1 million ARC challenge. Yeah. $1 million competition, the ARC prize. So the chance that we beat this with a version or a hybrid architecture using the Karpamambathy GPT repo and the Mamba 2 is pretty much zero. Usually these types of challenges, the way to win them is just with compute. It's kind of like Kaggle challenges where the people who win have access to like tens of thousands of dollars of compute and they're training on massive data sets. So like we're not going to really be able to make a dent here, but it's more just about trying something out, making a little contribution, and hopefully learning together. Okay. Hope your trip was good. I appreciate it. How's it going, Raphael, Tomcat, Eric, XYZ, Godbuddy? How much dollar I have to spend to train this model GPT-2? So I think in the Karpamambathy video, he says that you can train this. He uses a Lambda for cloud computing. So basically he's renting, I think, an 8x A100 server node, which is basically just a big GPU in the cloud that actually has a bunch of GPUs on it. So it's like a computer that you can rent that has like 8 GPUs on it. And it trains in an hour. And the cost for renting that computer for an hour is roughly $10. But realistically, right, that you're not going to be able to run this first time and then you get it, right? You're going to run into issues. You're going to end up debugging. So probably around $100 of cloud compute, and you can have you can end up running this script, but you'll have to try a couple times. $4,000, definitely less than that. Yeah. Do you have any ideas for optimizing program synthesis using LLMs? I had like a repo where I tried to do that. Actually, let me see. Hupo GitHub code evolution. I'm gonna have to search for it, but I made a project a while ago where I was trying to do that. I basically had LLMs generating code, and then I had them wrapped inside this kind of evolutionary algorithm where the code that was slow and didn't work get pruned, and then I had LLMs create variants from the code that did work. But I mean, it didn't really go anywhere, so. All right. Why don't we actually get started here, because I think I've set up the problem quite well. And now we're going to start. So first thing we're going to do, and I'm going to actually do this from scratch. So one thing that I did notice here is that actually if we open up the YouTube, the way that Karpamambathy did this stream, he's not actually doing it from scratch. So he obviously, like, he did all of this beforehand, and then this video is basically him copy pasting the pieces one by one, right? So it's like you don't actually see him working on any of these things. He just kind of like, he had it all before, and then he like copy pastes a section and then he talks about it. And I think that's actually a much better format than what I used to do, right? I feel like when I used to do these coding streams, it's just me literally coding for whatever, a couple hours, right? But the problem with that is that it's not very entertaining, and I feel like this is probably the better format, right? Where you have a bunch of the work already done, and then you just kind of copy paste it, and that's the video. So I'm going to be doing a little bit of that, but I also don't have all of it done, so most of the stream, at least the second half of the stream, and most of tomorrow is just going to be me actually just coding in a raw format. But maybe there's a use in that, right? There's a use in actually seeing how stuff is done rather than someone just kind of presenting to you the code that they've already written. So we're going to start from scratch. And the first thing we're going to do is you go to your GitHub, then you go to your repositories, and then you go here and you hit new. All right, we're going to create a new repo. We're going to call it Karpamambathy, which is a combination of Karpamambathy and Mamba. I'm going to say hybrid Mamba GPT, Mamba transformer on Arc challenge. All right. We're going to add a README. For gitignore, we're going to add a Python. We're going to search here Python. The gitignore is basically just telling Git which files you don't care about, right? So like random compiled stuff, images, like random crap that you don't necessarily want Git to be tracking. You can put it in this gitignore, and there's templates. So we want the template for Python. And then when it comes to licenses, really there's only two that you should be using because you should be publishing open source code. MIT license or Apache 2 license. I like the MIT license just because it's the OG, but I think the Apache license is a little bit more vetted by lawyers. I think it has extra protections around like you can't sue me kind of thing. But I just like the simplicity and the cleanliness of the MIT license, and it's kind of a vibe, so I just go for that one. All right, so now we have our repository. So we're going to hit Create Repository, and I have to select an owner. So here are all the different organizations. I'm going to make this a repo on my thing. And then I'm also going to make this a public repo, so all of you guys will be able to see this. All right, so now we hit Create. All right, so now we go. Boom, here's our repo. You can see the only thing it has in it is this license, which is the MIT license. Here's a nice little summary. You have the README and you have the gitignore. So we're going to come here and we're going to say clone it. So we want this in our local computer. So we're going to copy that. Then we're going to come here. We're going to open up a terminal. We're going to zoom in so you guys can see. Normally I don't work extremely zoomed in like this, but obviously I'm streaming, so I feel like you guys need to see the code. So I'm kind of working in like a boomer viewed kind of mode, but like I don't normally work like this, right? So don't judge me. So we're going to go into my dev folder, and here's all the different projects I have. And we're going to git clone this Karpamambathy. Okay, so now we're inside Karpamambathy, and you can actually go in there. You see we've got our license, we've got our README, and if you actually do that, you can see some more information about it. But there's nothing in there yet. Okay, so next thing we can do is we probably want to copy some of these files in here, right? So this is actually the one I was working on before. This is the one we want. So let's go over to Karpathy's repo, build nanogpt, and we're going to do the same thing. We're going to copy that. We're going to go one folder up, and we're going to git clone the Karpathy repo. Okay, so now we actually have the build nanogpt in there, and you see there you go, there's all the stuff. So let's go back to Karpamambathy, and let's copy over some of these, right? Let's copy over the train GPT-2, let's copy over HelloSwag, and let's copy FineWeb as well. Okay, so we're gonna copy build nanogpt train GPT-2, and we're actually gonna call it train. And then we're also gonna copy HelloSwag, eval. We're not going to necessarily need all of these, but it's going to be useful for us. And we're going to copy that here. And then we're also going to copy the FineWeb. Build nanogpt FineWeb there. All right, so now inside our repo, you see how we have FineWeb, HelloSwag, and train. And when we actually do git status, you can see that we haven't added these to Git yet. So you can use Git entirely through the command line, right? So you could do it this way. You could say git add dot. See, now we've added them, so now they're added there. Now we just need to add a commit. So we're going to say copy paste Karpathy. And then we can git push, right? And now if we actually go to our Karpamambathy repo, we refresh, you can see, boom, there we go. There's our commit. We copy pasted these 3 files. Okay. But that's kind of how you used to do stuff. Now, most people don't really use Git through the command line like that. Now you kind of use VS Code as your main development environment. So in VS Code, and actually here I have a specific profile that I use. Here you go, this is my profile. I like my bar here on the left. Let me actually make this big. Again, this is kind of obnoxiously big. Like, I don't think most people are going to be doing it at this size, but this is how we're going to have to do it for this stream. So I have some shortcuts here, right? So you can see here, this is the file view, so you can see all the different folders here. And then this is the git commit view, right? And I use shortcuts to jump between these. So the mouse that I'm using, let me see if you guys can see this, but the mouse that I'm using is one of these MMO like mice that has all these buttons here on the side. And I have a bunch of shortcuts on all these buttons, right? So I have Control Shift. So I have Control Shift 6, shows me this view. Control Shift 4 shows me that view. We'll see I have shortcuts for debugging too, like Control Shift 1. And in general, like, I'm a huge advocate for learning shortcuts and using them because I think it's a great way to speed up your workflow, and it also increases your neuroplasticity, right? So like learning new shortcuts, like it's kind of like learning piano or learning any kind of dexterous skill with your hands, where forcing yourself to learn different motor mappings on your hand will make your brain kind of, will put it in this kind of like learning mode, right? So I think if you want to grow intellectually, you need to also be growing physically. So the human body is a combination of kind of like physical skills and intellectual skills, and you can't really do just one, right? Like, it's counterintuitive, but if you're getting better at yoga while you're learning to code, you're actually going to do both of those faster. And constantly changing your shortcuts and learning new shortcuts is a way of kind of doing that, right? Because you're forcing your brain to learn a new type of motor mapping, and that puts your brain in this kind of neuroplastic state. And when you do that, it seems to me like it's easier to learn things. But I don't know, that's a little hack for you guys. Yeah, low FPS. Yeah, the setup I have here is not ideal. So the setup I actually am using here is I have my Linux computer, which is this one. This is kind of like my daily driver that I use for kind of work and any kind of compute or any kind of programming. But I don't have OBS set up on this Linux computer. So what I'm actually doing is all the camera, like all this stuff that you guys see down here and this camera and all this shit, that's all on a Windows computer. So I'm streaming this Linux computer to a Windows computer, which has all the OBS running. And then that Windows computer is streaming to a server box that I have. And that server box takes that stream and then sends it to YouTube, Twitch, and X or Twitter simultaneously, right? So I actually have 3 different computers in this kind of weird daisy chain setup right now. And that's why whenever I switch screens like this, you see how it's kind of like laggy? It's because it's literally streaming and then streaming again and then streaming to you guys. So it's not ideal. I think if I keep doing these coding streams, I'll figure out some way to have kind of the camera and microphone and OBS set up on my Linux computer, but Linux audio is just not very good. So right now I'm kind of using a kind of a janky setup, but hopefully you guys are okay with that. Okay. Question from Frank. AGI means AI doing things better than people. Yeah, AGI, really the pure definition of AGI is the general part, right? So the general in AGI, artificial general intelligence, means some kind of intelligence that is general, which means it can solve a lot of different types of problems. And this is why I say that we already hit AGI. To me, AGI was ChatGPT. The ChatGPT moment was AGI. The fact that you had a single language model, and that language model could produce poetry, it could answer medical questions, it could answer programming questions. That is the definition of AGI to me. But what happened is that we kind of moved the goalpost forward, right? So nowadays, when people talk about AGI, they're not really talking about the 2018 or 2010 definition of AGI, which is just have one model that works for a bunch of things, which we basically already reached with modern language models like ChatGPT. Now, when people talk about AGI, different people mean different things, but they're almost more talking about some kind of embodied, kind of like flexible intelligence. Like people have a definition of AGI that we're not going to get to until 2035, and some people have a definition of AGI that we've already gotten to, like myself. But yeah, don't focus too much on what is AGI and what is not, because at the end of the day, it's like as soon as we get to some point, people are just going to move that goalpost forward, and they're going to have a new definition for what AGI is. So, can you explain a bit how adding Mamba blocks may help improve GPT-2? Does it train faster, better self-attention, more efficient? It's difficult to say theoretically, specifically why these hybrid architectures work better. It's more of an empirical finding, right? So it's more all the people that have been using these Mambas, which are different in that they're called linear attention models, where basically they're not doing this quadratic self-attention, which transformers do, which is less of an inductive bias and allows transformers to kind of learn very well. These Mambas, which are similar to LSTMs or RNNs or things like that, right? They're kind of usually they have some hidden state that they're passing forward, which allows them to have a little bit, almost more of like a memory, kind of implicitly. So it's a stronger inductive bias, but it works well for time series problems, and they're also much faster in terms of inference because they're not quadratic with respect to the input length like transformers. But these hybrid architectures are an empirical finding, right? So basically people started playing with these ideas, and the first time I saw this was in this one here, Jamba model, was this. This was the first time that I saw this. This was a Jamba model. I think this was released. I forget who released this, but in this paper, they figured this out, or at least this is the first time I saw this, where they basically designed foundation model solutions. They had a GitHub about this. Here we go. Yeah, they discovered that if you actually mix Mamba blocks with transformer blocks, you get better performance than just kind of a classic architecture where you just have a ton of transformer blocks. That's kind of how deep learning works, right? You just kind of empirical findings, and then you just kind of, okay, that's why it works, right? So you can see here in this is Karpamambathy's code. You can see here how there's just a bunch of transformer blocks and however many of them you have. So in this case, there's 12 transformer blocks in a row. So what we're going to try to do is we're basically going to replace some of those with these Mamba blocks. So rather than having 12 transformer blocks, maybe we do alternating transformer, Mamba, transformer, Mamba, transformer, Mamba, transformer, Mamba. Okay. So let's go back to this code here. All right. So we copy pasted the code from the Karpamambathy repo, but now the next thing we want to do is we need to set up our local environment, which is usually the first thing that you have to do, and it's kind of annoying to do, and people have a hard time doing it. So I'm going to actually show you how to do this. So there's two different ways that we're going to do this, and we're going to document what we're doing inside our README, right? So this is kind of how I like to work. You put in all the commands that you're typing into your README, so it makes it easy to look at later. So we're going to have a local conda, and then we're going to have a setup Docker, right? So these are two different ways of doing dependency management. Dependency management is managing your dependencies. A dependency is basically a bunch of code that your project depends on, right? So anytime you're running code, right, all these little imports, this is basically some other code that someone wrote, right? So here you're saying, okay, well, I need Torch, right? Okay, so we need a specific version of Torch. So these solutions here will allow you to basically ensure that anytime anybody runs this code or tries to set it up on their environment, that they're using the same version of Torch that you use so that they can get the same results. All right, so we're going to be doing a little bit of cheating here because I already did this. Here we go, Karpamambathy Mamba practice. And here is the setup. So we're going to kind of copy paste this, and then we're going to kind of do it by hand to show you guys exactly what's going on. Okay, so set up local conda. All right, let's come here. We're going to make this like this. We're going to have this kind of set up like this. Oh my God, this is so large. All right, So first thing that we're doing here is you see that we're cloning the repo. So we already did this, right? We're already inside this, and we're actually gonna conda env remove Karpamambathy. Actually, let's ask ChatGPT. I already forgot. GPT is very good for this type of stuff. Conda remove environment command. There we go. Boom. Conda remove dash dash name. So the reason I'm doing this is because I already have this conda environment. So we're going to remove the Karpamambathy. Conda env list. Conda env list. What do we call it? Karpamambathy. This one. Okay. Conda env remove name. Okay, so we got rid of it. I should have probably done that before. The next line here, we're going to create a new conda environment, which is a Python-specific dependency management solution that you really only use for your local setup like this. And you can see this little base here. That basically means that I'm on the base environment, right? So whatever the kind of generic environment for your computer is. We're going to make a new one, which is called Karpamambathy, and we're going to say Python version 3.11. Right? All right, so there you go. Boom. It's going to go ahead and it's going to create that for us. Okay. And you can see here it says done, 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 all no problems here. And it says, okay, you can activate this with conda activate Karpamambathy. So I'm going to go ahead and paste that as well. And actually, the shortcut that I'm doing here, if you guys want to know, in Linux, I think this is Ubuntu, which is my favorite Linux distro. There's kind of a holy war when it comes to Linux distros. Some people shit on Ubuntu because it's kind of like the noob distro, but like I was using Ubuntu when I was just like a little kid, right? Like, and it was the first one that I used, and I kind of have an emotional attachment to Ubuntu, so I don't know. I just like Ubuntu, you know? We're going to activate that, and you can see here, actually, the shortcut I was going to say is if you highlight something like this, and then you click the middle mouse button, so you just click the middle mouse button, you click it down, it'll paste that. So that's a very nice little shortcut. I can just highlight something and then boom, click to paste, which is very convenient. Okay, but you can see now I've activated it, so now we are inside the Karpamambathy conda environment. And actually, if we do this, for example, you can see that now the Python that we're using is the Python specifically in Karpamambathy. So this is a specific kind of like isolated Python, and that's where we're going to be installing all of these Python dependencies. Okay, so this is going to be the big install here, which is Torch, Torch Vision, Torch Audio. This is basically PyTorch. And when you're installing PyTorch, basically this number here, this is your CUDA number, right? So I'm going to assume that you already have a NVIDIA drivers and you've already installed your GPU. And actually, we can go ahead and do that here. So let's figure out what GPU we're looking at. So we can say watch-n 0.5 NVIDIA SMI. And what this command is going to do is it's going to run NVIDIA SMI every 0.5 seconds. Right? So here we go. It's running every 0.5 seconds. All right? And this is basically the GPU I have here. So I'm using a NVIDIA GeForce RTX 3090, which is, you know, it's a little bit older, but I also have a emotional attachment to this GPU. You know, it's been with me forever. I have even older GPUs that I still use. So you don't need a big GPU to do machine learning development, right? There's going to be people who have money and they buy these big fancy GPUs and they have these clusters and server racks at home, and they're going to try to shame you for having an old GPU, right? They're going to try to pretend that they're better than you because they have a better GPU, right? But that's not the case, right? You know, there's plenty of people that have a really fancy, nice, expensive GPU and they just suck at coding. So don't let your poor GPU make you feel bad, right? Okay, so you can see it's got about 24 gigs of VRAM. So we're currently using about 1 gig of VRAM, and where is this gig of VRAM going? It's on these windows, right? So actually, like, the Chrome is going to take up some of that. The literal screen is going to take up some of that. So that's why it's not completely empty, because there's some screens here. There's some visual processes that your GPU is actually currently using. But you can see here it's using only 25 watts out of the maximum power limit of 350 watts at roughly kind of 10% GPU utilization. So it's really not being taxed heavily right now. Okay, so the other important thing here is you want this, the CUDA version. So the CUDA version that I have installed on this GPU is 12.2. So that means that when I'm picking the version of PyTorch to install, I don't want to pick a CUDA version that's like way different, right? I don't want to pick like a CUDA 11 or like a CUDA 12.5 or something weird like that. Just pick a CUDA version that's kind of around whatever you have on your GPU, and also pick a Python version that kind of matches that. And if you want more information on that, you can also do this, do Python CUDA versions. PyTorch, I think is what I want. PyTorch. Previous, something like this. Yeah, so you can see here, PyTorch has a bunch of these, right? So you can see how CUDA 11 probably intended to be used with specific, like, you can scroll down here and look at kind of what versions make sense together, right? So you can see, okay, maybe my GPU has CUDA 12. In that case, Torch 2.2.1 seems to work with CUDA 12, right? And this is kind of a trial and error thing. Like, you're probably going, especially when you're doing what we're going to be doing, which is combining multiple repos, because part of the difficulty is that this Mamba 2, right, you can see here it was tested with this particular setup, and the Karpamambathy repo was probably tested with a slightly different setup. So when you're combining different repos like this, and they use slightly different versions of PyTorch and CUDA, you kind of have to trial and error your way to pick the right version of PyTorch and the right version of CUDA for your system and for the repos that you're going to be playing with. Okay. But I've already gone ahead and done that for you, so we're going to just copy paste that in there. Okay. So there you go. Boom. It didn't really have to download anything because I already had downloaded this, so it's already cached somewhere. And you can see it's now using cached. So it's basically, it already downloaded this. It just needs to now install it into the specific CUDA or Conda pip location. Okay. There you go. Installed a bunch of other crap. You can see all this NVIDIA crap that it installed. NVIDIA Kudi Kupti, NVIDIA Kudi Kublas, NVIDIA Kudi Current. Right? So these are all just different CUDA things. CUDA FFT, CUDA RAND, CUDA RVTC. All right, so clear. We've installed that. All right. Now, we're going to install these two things. So TikTokin and datasets. These are basically dependencies for the Karpamambathy. So Karpamambathy here in Train GPT-2, he's using, for example, HelloSwag. He also uses TikTokin, right, which is like a tokenizer. So we're going to install those repositories as well. And a kind of a tip here is that generally try to pin these, right? So whenever people say, for example, pinning your dependencies, what they're talking about is using a very specific version, right? So I could just give you this README and I could just do something like this, right? Where I basically just give no version like that. And when you copy paste this into your computer, it's going to install probably a different version than I used. So I think in general, when you're publishing open source code, it's useful to pin these versions so that other people use the exact setup that you have, right? They're using the exact Python, they're using the exact CUDA, they're using the exact version of TikTok and datasets, and that's going to prevent these kind of dependency issues that people run into where they try to use some kind of repo, they end up not having the same dependencies, they end up getting these obscure bugs with random things that have changed in some of these dependencies, and it ends up being a huge mess. So in general, pin your dependencies. All right, so we're going to install that one. We're going to install this one. So now we've installed all the dependencies that we need for the Karpamambathy code, right? This train.py. But now we need to install all the dependencies for the Mamba, right? So the state spaces repo, right? And the way that we're actually going to do this is we're actually going to clone this repo into our repo. So we're going to come here and we're going to say code, and we're going to say copy. And then we're going to go into our Karpamambathy here. And we're actually going to clone this in here. So we're going to do git clone that, cloning into Mamba. And now, if we actually look at our thing here, you see we've actually copied that repo, and it's now inside this repo, right? So why are we doing that? Because now, in our train script, we can basically import it directly. So we can say import Mamba, right? And what this is doing in Python is it's actually importing this. So if we need to change anything in this Mamba repo, like let's say we do something here and then we want to change some little things here, it's very convenient to have this basically set up here locally so that we can just import it here and just mess with it as we will and not have to create our own fork and do any kind of fancy shit here in order to have our own slightly different version of this. So that's what we're going to do there. Once we do this, though, we don't want to be committing this, right? We don't want to have this necessarily committed. So what we can do is we can come into our git ignore and we can add it here. So we can say, we can tell git, don't commit this Mamba, right? So now if we hit control save, you see how this suddenly turned gray, this Mamba here? What that means is that git is not going to be tracking that. It's basically going to ignore all those files. All right. Now, Jesus Christ, Control KW. Let's go back to the README. We've cloned this repo. Let's install a couple dependencies that we need for the Mamba. So we're going to install those. Okay. And now we're going to actually pip install the Mamba itself. So just so we can have it as a repo here, we can do this. So we're going to go into the Mamba, cd Mamba, and we're going to do pip install -e dot, and that's going to install this, right? So it's actually going to be using this setup.py here to install a bunch of other shit that we don't necessarily need to care about, right? So if you can actually go here, it'll probably have a bunch of other crap that's going to be installed like this. Include tests, just whatever blah crap here. INOPS, Ninja, packaging, torch, transformers. So rather than kind of dealing with that ourselves, we just do the pip install -e, and that'll install all of that from that setup.py. Okay. The fuck is this? Delete. All right, let's see what you guys are talking about while this installs. I am planning to buy a 4070 or a 4060 laptop. Both of those should be fine. The VRAM, the more the better. Yeah, that's a good advice. So this VRAM here is probably the most important metric when you're buying a GPU. So the number, right, the number of the GPU, so the 4090 versus the 3090, what that means is that the 4090 is basically the next generation version, right? So the 1080s, 1070s, then there was the 2080s, then there was the 3090s and 3080s, 3070s, 3060s, and now there's the 40s, right? So even though this is an older generation of GPU, this is one of the biggest kind of VRAMs that you can get for this generation, right? So 24 gigs of VRAM means that you're going to be able to load up to 24 gigs of a model into your GPU, right? And if you're going to be doing training, you're also going to want to be loading your data onto your GPU because you want the compute that your GPU is doing during training to all be inside the GPU memory, right? You don't want to have some of it inside your CPU memory because then it's going to be having to put it into the GPU memory to compute things and then take it out of the GPU memory. So you ideally want all of your model and all of your kind of batch to fit within this GPU memory. So when you're buying a GPU, right, don't buy a 4060 that has like 8 gigabytes of GPU memory because that's not going to be as useful as a 3090 that has 24 gigabytes of GPU VRAM. So this is almost the most important number here is the VRAM. Okay. Any idea how bad of an idea it is to buy a used GPU? It can be a good idea or a bad idea. So when it comes to used GPUs, you kind of want to know what it was used for, right? So if you're buying a GPU that someone was using for gaming, that's probably fine, right? Because I don't think that person was gaming 24 hours a day for like 3 years straight, right? So that GPU is going to be pretty fresh. But if you're buying a GPU that someone was using for like Ethereum mining, that GPU is worn the fuck out, right? Like that person has been running that little GPU to mine Ethereum effectively 24 hours a day for the past 3 years, right? That GPU is tired. The fan is probably worn out. Like it's just not in a good state. So when you're buying used GPUs, try to determine how much that GPU was used, right? If it was just someone's gaming GPU that they had in a corner of their room and they like barely used it, that GPU is more than fine and you're probably getting a pretty good deal buying it from them. But if you're buying like a GPU from an Ethereum mine or some kind of situation like that where someone was running it pretty much 24/7 for the past X amount of years, you probably don't want to buy that GPU because it's going to be a little worn out. Okay. Okay, I think that's most of the questions. So this is still running. While that's running, we're going to copy this little script that I made. So I've made a little script. Not here. Here, sanity check. This one. Copy. Okay. So we're going to come here. We're going to make a new file. This new file is going to be called sanitycheck.sh. And this is a script, right? So this is not a Python file. This is just a script. And what this script is going to do is it's going to run NVIDIA SMI. Then it's going to run Python 3 version. Then it's going to run NVCC version, which is effectively kind of the CUDA version. Then it's going to run Python 3 with Torch, and it's going to basically print the Torch version. And then this is the most important part. It's going to run this torch.cuda is available, which is letting you know whether or not the PyTorch that you installed can use the GPU that you have on your system, right? So we're going to hit clear. Then we're going to chmod plus x sanity check. Sanity, not inside here, cd dot dot. Chmod plus x sanity check. And this is giving permission to run this script, right? So you're basically saying, okay, this script here, I want people to be able to run it. So that's what I'm doing there. And now we're going to, you see how it's green? That's because we gave it the run permissions. So now we're going to run this sanity check. Come on. Why does this not? Oh, because I didn't save it. There you go. All right. So you can see here it printed out NVIDIA SMI. It printed out the Python version 3.11, which is what we installed, so that makes sense, right? It also printed out NVCC, so you can see that that's 12.2. That's the CUDA version we have on our system. That's fine. The Torch version is 2.3.1 with CUDA 12.1, which is fine, right? Generally, if your version is off just a little bit, it's probably okay. But if this was like CUDA 12.5 or CUDA 11.3 or something like that, it would probably not work. So you want a CUDA version that's kind of close to what you have on your system. And then this is the most important one here. Torch.cuda is available true. So that means that we can use the GPU. All right. So sanity check is over. Let's go ahead and actually copy that as well into our README. So we're going to go back here, Karpamambathy practice. And you can see that in the README, I put all the instructions so that it's easy to try this again on your system. So we're going to sanity check. We're going to say sanity check and then tell people what command they need to use. -- sanity check .sh . Boom. Okay. Now let's actually test the dependencies by actually running train.py. So we're going to test dependencies. We're going to say Python 3 train.py. All right. And if we can run that, then it means that our thing is set up correctly. Okay, so the problem here is that it couldn't find this data set, right? So this is good because it didn't fail here, right? If it would have failed at any of these imports, then it basically means that we did our dependencies wrong. But it didn't fail until line number 227, right? So we scroll down to line number 227, right here, os.lister data root. So it was trying to find this particular folder and it couldn't find it. So basically this is the data set. Karpamambathy provided this script, which basically downloads this data set, but it takes a little bit of time to run, so I already had it ready to go. So I'm going to actually copy from my practice repo here, Karpamambathy. I should have probably named this something that's a little bit easier to type, but Mambathy practice. And we're going to copy edufindweb to here. Okay, so now you see we've copied over edufindweb. Let's also copy over the other folders. Come on. You can see even just copying it over takes a bunch of time because this is a data set. It's a sharded data set. So you can see it's just a bunch of .mpy files. Still copying, still copying, still copying. It's actually quite a heavy data set. So you can also do this Nautilus dot. That'll open up this kind of Windows viewer, and you can click on this and you can say properties. And you can see here, this is 20 gigabytes of data. This is quite small. You probably can't see that. Okay, but the other couple things we want to copy are going to be, I think we have them here in our gitignore, HellaSwag and edufindweb. So we have the edufindweb. Let's also do the same thing for HellaSwag. HellaSwag. Okay, that one was a lot smaller. And you see how they're green here? They're green because VS Code wants to add them. It's saying, oh, okay, you want to add this? You want to git commit these 20 gigabytes of data? And the answer is no, I don't want to git commit 20 gigabytes of data. So what I'm going to do is I'm going to go into the gitignore and I'm going to say ignore edufindweb, edufindweb 10b, and also ignore HellaSwag. All right, and when I hit save, you'll notice that these will turn gray, which is what we want. Because now, if we go to our git commit, you see, it's not adding that at all. Okay, so we've added some stuff in here. Let's actually go ahead and save this. So we're gonna just commit this to our repo, and we're gonna say local conda setup. Add that, boom, commit, sync changes. Okay, and now if we actually go back to our repo here, you'll see right now there's nothing, and then if I hit refresh, boom, there you go. Now we have our setup local conda with our dependencies. We're looking good, guys. We have our little local setup, and actually if we run Python 3 train now, it should no longer fail. And you can see here, boom. CUDA out of memory. Tried to allocate 12 gigabytes. So we're actually going to run this, and we're going to look at the memory when it does this. So let's go ahead and do Python 3 train, and we're looking at this number here. So you see how it instantly flashed to like 23 gigabytes, and then it crashed? So basically what happened is it tried to load the model, and it tried to load the batch, and it basically ran out of memory. Because this script, which was written by Karpamambathy, he was running it on a bigger GPU. Right, so we're going to have to run this on our shittier, smaller GPU. So in order to do that, we're going to have to reduce the batch size. So in here, we're going to have to find the batch size somewhere over here. No, right here, probably where that. Let's see if we can. I think he called it capital letter B, and we're going to click this so that it only does the capital letter B. There we go. B, 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 B. It's usually by the data loader. Oh my God, come on. B equals, nope. What about here? Here we go, boom. Total batch size is this, and then the micro batch size, well, let's make this 2. 2 is always like, if you're running to CUDA memory errors, try a batch size of 2, and now let's run it again. Okay, so at a batch size of 2, now let's look at the memory. Went up to 3 gigabytes, and it's working fine. You see that? Okay. So 3 gigabytes is not too much, so I think we can go a little bit higher than that, right? Let's try 8. So we can do 8. Save that. Run it again. And let's see what we get to. 4, 7. Okay, so now we're at 7 gigabytes out of our 24. That's a little bit better, right? We're getting a little bit more utilization. You can see our power went up as well. But we can push that even harder. Let's Control C. Let's do 16. Run it. All right, 16 gigabytes takes us to, or batch size of 16 takes us to about 12 gigs, which is more of what we want, right? The more we can increase this batch size, the faster this is going to train. Let's actually do 32. Really testing it. I think this is going to be probably the limit. Looking at this number here. Boom, perfect. 22 gigs out of 24. So I think that's our batch size. We're going to be using a batch size of 32. And you can tune that for your GPU. And this is the micro batch size, which is basically kind of like a fake batch, right? When they train these systems in these distributed cloud setups, they're using much bigger batch sizes, and they're kind of accumulating these gradients for all the different computers. But when you're running it on a much smaller GPU, you can't load that entire batch all at once. So what you do is you do these micro batches where you basically do little tiny versions of the total batch size until you have the full batch, and then you push the gradient for that, right? So you're still going to get the same, like, mathematically equivalent thing, but it's going to basically be doing it in chunks like this. Okay, so it actually ran out of memory as well, which means that later on, even after you loaded the data, it tried to load something else and then ran out of memory. So we're actually going to go back down to 16. Okay. Let's run that. All right. So now we have that. Let's do a little bit more dependency management. So we're going to Control KW, close out of that. We're going to go back to our README. And now we're going to do our Docker environment. So this is kind of running in the background. I just want to check, make sure it runs and it doesn't run into any GPU out of memory situation here. So it's waiting. It's probably loading the model at some point. We can see at some point this is going to probably get bigger. It's doing something, right? Another thing I like to open up while this is open is you do Control-Alt-T and then you do GNOME System Monitor. And this is useful because it shows you the CPU. So this computer has 24 core CPU, and you can see the memory. This is the CPU memory, or the RAM as it's known, and the VRAM would be here, right? So this is the VRAM. So you can see 21 gigs, and it's training. There you go, boom. So this is fine. You can see it's using up the CPUs. You can see how it's like alternating. So not all the CPUs are working at the same time. Some of them are working more and some of them are working less. And then here you have the total amount of memory being used is about 14 gigs on the CPU, about 20 gigs on the GPU. And the GPU is basically maxed out here. You see 100% GPU utilization, 348 watts out of 350, and maxed out on VRAM. So I think this is probably good for our system. We're actually going to Control C because or else the computer might explode, right? It's trying to stream at the same time. Streaming at the same time is fine because the streaming isn't using the GPU, the streaming is using the CPU. But I want this to be a little bit smooth, right? So if you're training on your GPU, generally everything starts to slow down, so we don't want to be doing that live. All right, let's look at, you see this log folder here? I don't want that in Git, so I'm going to add that here as well. Let's add the log folder there as well, and then boom. You see how that got ignored now? So you don't want to be like committing logs and data sets and shit like that, so let's do batch size for 3090. Okay, actually it's a micro batch size. All right, so now that we have the right batch size, go ahead, commit that. And let's do the Docker dependencies. So Docker is basically the big boy version of Conda, right? Conda is a dependency management solution, but only for Python, right? So it basically just does dependency management, but only for Python. And ultimately we're going to want to run this on some kind of cloud setup, or we're going to want to run it on a different computer, right? Have a different computer that has different GPUs. And we don't want to have to do this for every single one of our computers, right? It'd be kind of annoying if every time I logged into some AWS machine, I had to like run this installation again. Or if I went to a different computer that I have at home, I'd have to run this again. I don't want to have to do that. So there's something called Docker, which is basically just a more complete dependency management solution where it kind of simulates an entire computer. So it's kind of like a fake computer that you can create and then put all your dependencies, set up all your dependencies inside that fake computer, and then you can just go to any other computer that has Docker and say, okay, I want this exact fake computer. And that's quite convenient. So in order to do that, we're going to have to basically create a new file here, and we're going to call it Docker file. And you can already see how the little logo changed. So VS Code already knows what a Docker file is. It's actually quite a common type of thing to find. And you can see how the Python files have this little Python symbol. The Docker file has this little whale that's kind of like a container ship. And containers is the name for that fake computer that I'm talking about. So that's where that comes from. So the way that Docker works, we're going to copy paste the Docker file that I already had, but we're going to kind of go through it and kind of show you what each of these different things are here. Okay, so this Docker file, we're going to be starting from this, right? So there's basically the convenient thing about Docker is that there's what's called registries. So if I type this, right, there's this, for example, Docker Hub. Docker Hub has a bunch of Docker files that other people have already created for you. Right? So if you wanted to have a SQL database, here's a Docker file that already has all the dependencies and all the different little config shit done for SQL, right? So rather than starting from a blank computer, we're going to start from a computer that someone's already kind of figured out some of the shit for you. So we're going to be starting from this one here, NVIDIA CUDA 12.1 Devel Ubuntu 22.4. So this is basically a fake computer that is running Ubuntu 22 that uses CUDA 12.1, which is similar-ish to our CUDA, right? You don't want to choose a Docker container that has a very different CUDA version than the one that you're running locally. There's sometimes you run into issues, so generally try to pick one that has kind of a similar-ish CUDA version than the one that you have, right? And it's also made by NVIDIA, so they have all the kind of one weird tricks. They put it all on there. All right, next thing we're going to do is we're going to install Python 3 on it, right? Because this is a fake computer. There's nothing on it right now. So you need to literally install Python. Here's some crap to basically point the right version of Python, some other crap here for Python. And then here, you actually notice this is exactly the stuff that we did before, right? So it's going to be installing PyTorch. It's going to be installing TikTok and datasets, the two things that we installed for the Mamba. We're going to get into Wanby after this. And then you see here, we're going to be doing the same exact thing, git clone, pip install Mamba, and then we're going to run python.py. Okay, so now we have our Docker file, which is defining this fake computer, but we need to actually build that into a container. So we're going to go, I think, close out of that. Back to here, back to the practice. All right, build the container. So let's copy this command, and we're going to say build the container. Bash, bam. Okay. So what this command is saying is it's saying, I want you to build a container with this tag, Karpamambathy practice. Let's get rid of the practice. We're going to call it Karpamambathy. And we're going to say, we want this specific Docker file here, and I want you to basically run it in this directory. Why do we need this? The directory that you build this from matters, and why does it matter is because when you do this dot right here from this copy is looking at, it's going to copy over all of our code here. So because of that, we actually need to be a little bit careful. We need to also have kind of the equivalent of the git ignore is we're going to have a similar kind of thing called a Docker ignore. So we're going to actually copy paste that from here. Docker ignore, this one here. So we're going to come over here. We're going to make a new file. We're going to call it .docker ignore. And you can see how VS Code also recognized a .docker ignore, right? And says, oh, okay, I know what this is. This is a Docker file. This is a Docker kind of specific file. So we're going to paste that in there. And you can see that I added, for example, the license, the README, the Mamba repo, the Hella Swag, the As You Find Web, Wannabe. So like, I don't want the README, right? When I'm running this in some kind of cloud computing environment, I don't really care if the README is there, right? Because I'm not going to be like using that README. So I'm telling the Docker ignore, when you copy over all these files into this Docker container, don't bother copying this crap here, right? Don't bother copying this data set or this Hella Swag. We'll deal with that later. You don't want to be like putting your data set inside the Docker container. You want to link it in later, but we're probably not going to get to that point just yet. So we're going to do that, and we're going to build this Docker file here. Okay. So you can see it, I already had this pretty much built. That's why it built so quickly. But on your computer, this might actually take some time because it probably has to download this container here. All right. But now that we have this Docker container, we can also run the same sanity check. Go back here. Karpamambathy. Let's go to the README. Here we go. Sanity check the container. Copy. So we're going to go here, do sanity check, bash, paste. And actually, let's, before we even do that, let's just run our container. So we can come here and we can hit this. So the command that we're running here, we're saying docker run, and this is the container that we're running. We're also telling it use these GPUs and also remove this container when you're done with it. Okay, and then we're going to say bash. So now we're actually in the fake computer. So the same way that you can SSH into a different computer, now we're basically inside the computer. You see, we're inside this little fake Docker computer. And we can actually do this. We can say docker image ls. And you can see, this is the one that we just created, Karpamambathy. We can see it's about 13 gigs. Which is a lot, but it has all the CUDA, it has all the Python, it has the Mamba, it has PyTorch, so like that's why it's kind of big. But we can also do this, docker ps. And these are the ones that are running, right? So this is telling you, hey, this image is running. So we're inside of it right now. We're inside this little fake computer. And we can actually do all of our same things here. You can see, boom, look at that. Here's our code. We're inside a little fake computer. You can say, who am I? Root. Right? So that's different than if I say, who am I here? Who am I? I'm oop, right? In this computer, the user is called oop, but in this fake computer, the user is called root. Okay. So we're going to actually exit. And once we exit, we should be able to do this, and you can see how it's gone, right? And the reason it's gone is because we added this --rm. If we don't add this --rm, it'll keep running. So you got to be careful and check your Docker containers. Make sure you don't have random Docker containers running, right? Because that's just leeching from your computer. Okay, so now rather than actually going into the computer, we're going to just run sanity check. So we go like this, we run that, and that'll run the sanity check inside the Docker file. And you can see here inside the Docker file, you can see you've got the CUDA version. It's using GPU 0, so it's the same GPU. You can see the CUDA version is here, the Torch version is here, CUDA is available true, so this is good. See, look at that. CUDA version 12.1, which is the one that we installed. Or not the one that we installed, but the one that we used here, right? So notice that when we run this on our computer, it's different CUDA version, right? Because now we're inside the fake computer. That's why this CUDA version is 12.1 versus if we run the sanity check here, see how we get a different CUDA version? Because this is the base computer, and this one here is the fake computer. But really what we care about is this last one here, right? We want to make sure that inside the Docker container, we have the GPU is available. Okay. And we can actually do the same thing we had before. So we can say test ensure train works. Bash, bam. All right. So now we're going to be doing the same thing. We're going to be saying docker run with the GPUs, remove it. I want to run this particular Docker container, and I want you to run Python 3 train.py once you're inside that Docker container. So we're going to paste that. And, all right, boom, that's going. And you can actually see, since we've already tuned the batch size, there we go, to 12 gigs, and then it'll go to 22 gigs like we had before. Give it a second, it's loading the model. I think it loads the data set and then the model. That's why it does 12 gigs and then 24, or I don't know. Maybe it loads the model and then the data set. It just depends on how you have it in your Python code, right? So actually, we can figure it out. You see, this is where it actually creates. Yeah, so it's the data set first and then the model. See, it'll blast up to 22 here in a second. You can see how look at the CPUs right now. The CPUs are going crazy, right? But the GPU is just chilling, 12 gigs. Boom. Okay, there you go. Loaded the model. And now it's training, and you can see boom, 22 gigs on our VRAM. So now we're running train.py inside a Docker container, and it is using the GPU on our local computer, and it works. So let's Control-C out of that and clear. And let's go ahead and copy some of these commands too. Let's get the wanb working as well. Okay. Ensure wanb. We don't actually need wanb until we actually start training things, but okay. I think now would probably be a good time to commit. So let's Control-Z, Control-Save, 4. Okay, so you can see these are the things that we're adding. We're adding this Docker ignore, we're adding the Docker file, and then we're adding the instructions on the GitHub, or on the README. Okay, so we're going to say Docker, no caps lock, Docker setup, plus commit sync, and boom, now if we go to our Karpamambathy, hit refresh, there we go, there's our Docker, and here's our instructions for Docker. Okay, and that's pretty much all the dependency management stuff. So, you know, the dependency management is not super fun, you know, like people don't necessarily like showing that, but it's honestly the most annoying part about all of this, right? Like getting your dependencies right so that you can develop locally with Conda and that you can eventually run this on some kind of other computer or some kind of cloud environment with Docker. I feel like a lot of times this is what people have the most trouble with. So that's kind of what I wanted to start with, is this dependency management so that you can have it running on your computer with as little issues as possible. All right, I'm going to take a pause here. Okay, you guys are still talking about GPUs. People love to talk about GPUs, is what I'm realizing. Using Apple. Yeah, I haven't used Apple for a long time. Like, there's been certain tech jobs where my daily driver was a Mac, but back then, the Mac chips were just not good. So generally, the workflow that I had when I was a MacBook user was generally I used some kind of cloud environment. But my preferred workflow is this, where you have a Linux machine with a consumer GPU on it, and you do all your shit there. And then if you want to get fancy and do distributed training like Karpamambathy was, then you actually go to the cloud. There's a lot of different cloud providers. I think Karpamambathy recommends this one, Lambda Cloud. But it's also because they're paying him, right? So like these guys here, Lambda, they're a startup. They need money. They need people to use their service. So they're like, hey, Karpamambathy's going to make a video. Why don't we message him on LinkedIn and send him a DM on Twitter and say, hey, we will pay for your compute if you tell people that you're using our service, right? So you could use Amazon, you could use Microsoft, you could use Google. Like there's a million different cloud compute providers, and generally, in none of those cloud providers are you paying the real price, right? So like the prices for these things are not like actual prices. They're basically fake. And what I mean by that is that they're not like, it's not a mature type of setup where they know, okay, this is how much the GPU cost us, this is how much energy it's using, and therefore we're gonna do plus 10%, and then that's the price that we give you. All of these things, they're fighting with each other for market share, right? So all of the companies that give you cloud GPUs, they're kind of usually subsidizing these prices a little bit in order to get you to lock in, right? So they give you here, NVIDIA H100s are now available. So if you go on Lambda Cloud, you can get a little NVIDIA H100 and run your stuff there. And they're like $2.49 at an hour, right? Which seems pretty cheap, but they're probably losing money on this. And the reason that's okay is because if you get very comfortable with Lambda, then you're going to be using Lambda. And then maybe in the future, you go to a startup and then you decide, hey, we're going to be using Lambda at this startup. And then once you're an enterprise user, now they're going to actually give you the real cost, right? So a lot of these clouds are basically giving you these like weird subsidized prices. It's kind of like credit cards. You know, like credit cards, they always have like, oh, if you the first $500 is free, right? Or like some kind of shit like that. Like all the cloud providers do that. So if you actually want to be super cheap, what you can do is just do all the clouds, right? Go on Lambda and just kind of max out all the bullshit like subsidies that they do. And then once they kind of start hitting you with the real prices, then go to AWS and max out all the free shit that they give you. And then once they start hitting you with the real prices, go to GCP and then max out all the shit that they're giving you. So it's kind of like, I think credit cards is the best analogy, but it's like if you want to play that game of like paying the least possible for cloud computing, you can get pretty far. And there's people that are constantly switching the clouds and like finding all the weird, like if you go to a hackathon, maybe they give you 10,000 free credits and then you go to some other thing and they give you more credits. So like you can play that game if you really don't have a bunch of money and you want to be training on stuff in the cloud. But I don't have time to play that game. I just think it's easier to just have a little GPU locally. So that's kind of what I do. Yeah, Paperspace is another one. Let me spit out this gum. It's hard to talk with gum in my mouth. Okay. All right, so we've set up our dependencies, and now we can actually do the fun part. Okay. So this is where I no longer have things to copy paste. I'm just going to be doing this live, right? So I've never done this. I'm just literally doing it live right now. So we're going to need to find the block, right? Like ultimately we want to create this hybrid architecture, and we're going to need to replace these blocks here. So this line right here, right? Block config for range and config and layers. So in order, we're gonna want to basically do this. You see this list here? So let's pull that out. We're gonna do this, and we're gonna say block list is that, and then here we're just gonna say block list. Right? And by pulling that out, oh shit, we have to pull this over here. All right. So in order to replace, let's do this. Rather than doing this, so like whenever you do a list comprehension like this in Python, it's no faster than just literally writing out the for loop. So we're just going to literally write out the for loop. So we're going to do for I in range config and layer. So block list plus, and we're going to say block config, or not plus, we want dot append. And then we're also going to say block list dot append, and we're going to have our Mamba block, right? But now we need this Mamba block. Okay, so let's go get this Mamba block. Let's go into the state spaces, into their repo, blah, blah, blah. Scroll, scroll, scroll. Here is the Mamba block 1, but we don't actually want Mamba 1 block. We want this one, the Mamba 2 block. Okay, so let's copy this Mamba 2 block here. Copy, and we'll put it here. All right. And you can see that it doesn't know it, right? See how there's some red here? What VS Code is telling us is telling it, I don't know what the fuck this Mamba 2 block is. So we're going to say, okay, well, actually, you do know what that Mamba 2 block is. We want from Mamba import Mamba 2. Is it? Oh, from Mamba SSM import Mamba 2. There you go. And let's change it. So you see how VS Code right here is kind of giving us these weird, it's saying, I don't know what this is. I don't know what the fuck this is. I don't know what this is. And the reason it doesn't know what it is because it's not using the right Python. You see right here, it's using -bin-python3, which is kind of like the base Python. We want specifically this one. So we can click down here and then we can go to this one and that'll say, okay, I want you to use the Karpamambathy Python, which is the one that we're going to be using for local development. So you see how now all of these turn green? And if you actually go here and if I control click, see how this is Mamba SSM? So it's actually the Mamba right here, right? So if we go to Mamba 2, look at this. Mamba SSM, modules, Mamba 2. So it's literally this file here, which is exactly what we want, right? We could actually say print, we are using our Mamba 2, right? And then if we go here in our train, we can put a little breakpoint there. Control-Shift-1, Python debugger, Python file. That'll run this file, and it's going to hit that breakpoint. But right before it hits that breakpoint, blah, 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 and then let's put a breakpoint there. Boom, you see, we are using our Mamba 2. Okay, so you see how when it imported this, it ran into this print statement, so we can get rid of that. Okay. All right, so now we're using the right Mamba, so I have another shortcut for stop. So I have Control-Shift-1 to start debugging, and you can see here at the top it's debugging, and it'll go into these breakpoints, and then I can Control-Shift-2 to kill out of that, right? So it just makes things a lot faster to have these kind of shortcuts. And that's not even like an original idea, right? People have been doing this for a long time. Like if you know any kind of Vim or Emacs people, like they have their own set of shortcuts that they know. And I don't know, I'm just a big advocate for shortcuts. Okay, so you can see now that we no longer have this error where it doesn't know where Mamba 2 is, but it doesn't know what the fuck this is, right? So it's like, what is dim, right? So model dimension D model. Okay, well, we have this config object here, right? This config object contains this config here, this GPT config. So we need to add something in there, right? Let's do Mamba dim D model. This is going to be an int, and we're going to have that 768. Why not? Okay, let's put that in there. Put that in there, or config dot Mamba D model dimension D. Actually, you see here. Here's a little problem with Karpamambathy's repo is that you see how this is white? The reason this is white is because VS Code doesn't know the type of this config object, right? But we actually do know what that is. So we could actually do a little trick here. And if you do this, now what we're telling Python, this config object is a GPT config object. The GPT config object has these things here. So this should have fixed that. No, because you see here, he's using the config. So really you want this. Boom. You see, now we put self.config. Now VS Code, okay, it knows this self.config is this thing here, which is of type GPT config. So it knows to be able to look here and say, okay, this thing has a property called Mamba D model, which means that this is blue, right? So you could do that, have it be blue, but you could also not do that, right? So this is one thing to kind of think about here is that there's a million ways to do things in programming, right? And different people have a different kind of coding style, right? So right now, we're in Karpamambathy's code, right? So this is pretty much Karpamambathy's code written in his style. And you can see that in his style, he basically never really uses typing, right? Like if you look at, for example, the data loader or something like this, or even here, the batch sizes, right? If I was writing this from scratch, I would probably type this like this, right? I would probably put these ints, int, because that makes it more clear to the person writing and reading this code that it's an int, and it also allows Python to know that, okay, this is supposed to be an int. But some people don't like to do this because it kind of clutters, it visually clutters your program, right? They prefer this, where, hey, you don't have to type, but it's like cleaner, right? And even just the comments, right? Some people kind of prefer the comments like this, like that. But here's the tip I have for you guys, is that I used to be much more opinionated, right? So when I would write code, or when I would take somebody else's code, I would constantly be trying to like take that code and massage it into my particular style. But the problem with that is that you spend a lot of time just kind of like refactoring, just modifying the code with no real like value add to that. So now that I'm kind of older and more experienced, usually what I do is I just try to stick to the style that is there, right? So rather than say, okay, well, this is white, therefore it's bad, therefore I need to be typing this and blah, like, sure, but it's also just, hey, just learn how to live like this, right? Embody Karpamambathy, live in his mind and use his coding style and see if you can understand why he has a particular coding style. And I think that for me, it's like very clearly, it seems like Karpamambathy just loves this like minimal style where it's just all very minimal. You see how all these comments are like lowercase, lower, like he has a particular style. So I'm just going to use that style when I'm in his repo, and whatever. If I get tired, then I can make a new repo and I can have it be my style, but try to live other people's style and try to understand kind of why they have that particular style, and maybe you'll learn something. Okay. All right. But now we have our block list. It's a bunch of blocks where it used to be a bunch of transformer blocks. Now we're basically alternating these blocks with these Mamba blocks. And let's see if this runs. All right. So let's go to our train. We'll hit run. Seems like it worked fine. So we can actually compare. Let's do this. Let's do Control C, and then let's comment out this. Because right now the problem is that we have twice as many blocks as we had before. So the total size here is 168, 124. So this is a better. Now let's do this. We want to alternate. So we're going to say if I mod 2 is equal to 0 to that, else this. Okay, so now basically we're going to be alternating these blocks. And you can see that just with the pure transformer blocks, we got 124 million parameters. Let's see what we get if we alternate these. What's wrong? Oh, there's a little thing here. Okay. Okay, boom. So actually you can already see this. Look at this. If by alternating the Mamba and transformer blocks, it's already smaller. So this is now a 103 million parameter model versus 124 million parameter model. I don't know, is this big enough to see? Can you guys see this? Do you know what is my configuration? Yeah, it's a 3090, but I do have a 4090 actually behind me. I have a bunch of different GPUs. 4X 4090 is probably the best kind of local setup you can get. It's very difficult to work without types. Yeah, if someone comes from like a C++ or kind of like there's languages like that are explicitly typed, like they almost force you to type. So you can actually tell kind of what someone's background is, right? When people come to machine learning from a data science background, you know, they generally don't type. And then whenever people come to machine learning kind of from a more formal programming background, you'll actually see them type a lot, right? So it kind of lets you know their background a little bit based on their coding style. But again, I'm not going to try to put this in my style. I'm just going to use Karpamambathy style. Right? Think of it like an artist, right? Like if you're an artist, there's probably a style that you like to do. Maybe you're good at like anime style drawings, but like if you're in a class where you're doing kind of like oil painting fantasy art, you don't want to just do your anime style there, right? You want to kind of learn how to paint in a kind of like a oil painting fantasy style, right? So it's the code is kind of the same thing. It's like you want to be flexible. You want to be able to read and parse code that is written in a lot of different styles and try to write code in the style that you're in the style of the code base that you're in. And when you do that, you kind of get better at just reading and writing code in general. Just you can generalize more to other weirder coding styles if you run into them. And sometimes I just write weird styles anyways, right? So actually, I have my own weird setup. So like this repo here. So if you guys remember this project, the Zero Shot Autonomous Robot project, this is almost like the Jackson Pollock of coding styles. Like this is fucking weird style that I was just like on a vibe. And like, look at this. The repo is called O, and the main file is called o.py. And then when you go into these nodes, all the nodes have basically little short names. And like when I do the models, I also call them Gem, GPT rep. If this is for Gemini, GPT is for OpenAI. So like sometimes I just write in a weird style just to kind of change the flavor, right? But like, I don't know. I like the style I put in this one just because it was really cool. Iggy next test. All of these are just really weird. Let me see if I can find some more weirdness. Nodes. Goal. Yeah, this repo was fun because I also used a lot of emojis. So there's constantly emojis everywhere, which is pretty cool. You can literally put emojis in Python code and it just puts these Python codes. Everything was these like asynchronous loops and it's just like this massive, like, I don't know. I'm proud of this one. Like I said, it's kind of like the Jackson Pollock of like coding styles, but it was fun. All right, we're here. We're here. We loaded our alternating model with 103 million parameters, and yeah, kind of seems to be working pretty clean. So right now, what I would probably do is I would probably just run this. I would run this with and without this full blocks versus just Mamba 2 blocks, and then I would see how it works with the HeliSwag, right? So see what the difference is when you're training this on using Karpathy's versus just the Karpathy's pure transformer block architecture versus this hybrid architecture. See what the difference is. But the problem is that, right, this is a live stream. I'm not going to sit here and just watch this train. So I kind of need to find something else to do. And let's see what else we can do. I have some ideas. Let's go back to this. Upo, repos, practice. I wrote down some like to-do list of stuff we can do. Fork SSM, we already did that. Make public repo, sanity check, replace Mamba blocks, change micro batch size, we did that. Hybrid model with Mamba, I think that's what we're doing now. Test locally, we did that. Data loader with this. Okay, so now we're gonna get into kind of the gnarliest part of any machine learning project, which is the data loader. So if we go into the train.py here, blah, 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 where's the data loader? This it is. Here it is. Okay. So the data loader, actually, let's commit first of all. Let's go here. Let's commit this change. Train.py. We're going to say hybrid arc. Okay. Now let's go Control KW, clean out, Control 6. Close out of this. Train.py. And you can actually, there's an even better shortcut for that. You can do Control Shift P or Control P, train.py like that. Control W to close, Control P, train.py. Okay. This data loader light, this is the abstraction that is basically going to load your data and then feed it to your model, right? So when you're actually training your model, you're going to be sampling batches of data from your data set and feeding it to your model. So right now, this setup is an LLM setup, right? So basically what Karpathy was doing is he's training this thing from scratch on this Edu FineWeb 10B, and then he's evaluating on HelloSwag. So if we actually look at the training code here, he has this DDP, this distributed data parallel, because he was training it on like an 8 GPU node. We don't actually care about that. We can leave all of this stuff in here, right? Because then we will just get it for free once we want to put this on a larger system. But right now it's a little bit confusing because he has a bunch of like conditional logic based on whether you're doing this DDP stuff. But okay, here you go. You're setting the seed. Here you're making the setting the device to the CUDA, which is your GPU. Blah blah blah. Tick token. Get encoding. GPT-2. Here's your batch size. Here's your train loaders and your data loader. So why don't we comment this out? Or we're going to copy, paste it, and then we're going to say arc data loader, right? Go here. I don't think we need the light. We're just going to call it arc data loader. So let's go up here. We're going to copy this entire thing. And you see here how, here's another little code style thing, is that Karpamambathy, like it's like traditionally you would probably have all of these things in separate files, right? So normally, like maybe 5 years ago, you would probably have different files for each of those, right? You would have a model.py, you would have a blah, blah, blah.py, you would have a blah, blah, blah.py. But more and more, I've started doing this as well, where you just put everything into one Python file, right? And why are we doing that? Why are we just putting everything into one Python file? The reason we're putting everything into one Python file is this, so that we can very easily go Control-A, Control-Copy, then go to ChatGPT, and we could just do this, right? So if you ever run into any issues and you're going to want to debug with GPT, right? This is just part of the reality of being a developer in 2024, is that you're going to be copy pasting shit into GPT. So if you had everything shotgunned into a bunch of different files, you would then have to basically go into these different files and copy paste into GPT. And that's like a lot slower and a lot more annoying than just having everything in one file so that you can very easily copy paste, and then GPT has everything that you have, right? It knows all of the different parts of the code. So this is the reason why I kind of like doing this as well, but I don't know if this is the reason that Karpamambathy likes doing this all in one file. I think it's also he wanted it all in one file just because it would be all in one file. But I kind of agree with this particular code style. So we're going to go here. We're going to make a new little section, just copying his formatting here. And we're going to say arc data loader. Data loader for arc challenge. Oh. Okay. And we're going to copy paste this. Boom. We're probably not going to be using the TikTok thing, but all right, and we're going to call this arc data loader. Perfect. Okay. So now you can see it's no longer red, but we're going to have to kind of understand this arc data loader here. Abstraction and reasoning corpus for artificial general intelligence. Contains the tasks, data training, data evaluation. Tasks are stored in JSON format. Why don't we clone this? Why don't we do this? Copy. We're going to come here. We're going to say git clone that. So luckily for us, Cholet designed this so that it's really small. You see how fast that was, right? So it wasn't like this EduFineWeb, which like I basically ran overnight. This ArcAGI, the whole point is that it's supposed to be quick to download, quick to train. So that's also why I chose to do it for this video. So we probably want to add that to our git ignore. So let's go ahead and add that there. ArcAGI, like, nope. ArcAGI. Save. Now it's going to turn gray. Perfect. Okay. And let's actually look at what this looks like. Tasks or each JSON contains a dictionary with 2 fields. Demonstration input and output pairs, typically a list of 3 pairs, and then the test input and output, this is a list of pairs. Okay. Grid control, this is what they look like. Answer validation, here's what we're going to do. Arc challenge data loader. I bet you someone's already done this. Data loader PyTorch. EDA plus PyTorch CNN. Okay, so here you have someone who did it with the PyTorch. Here's on Kaggle. We could probably find blah, 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 for task, test path. Okay, cool. They're just doing some exploratory data analysis here, but I want to get their data loader. Here you go. Boom. PyTorch data loader. So we're going to be looking at this. Init, this is not good. You see how he's using a global variable for that? You probably don't want to do that. See, this is a weird coding style right off the bat. Like, as soon as I have like capital letters and lowercase letters like that, that triggers me. Let's do this. Copy. Put that here. Actually, it's not like, this is the problem with like coding in a very zoomed in way that is like very difficult to fucking see anything here. Get new matrix, self-stage, train, get new matrix, repeat. I don't think we need much of this. BT, this is the batch size. Why don't we change this? This is going to be arc, AGI, data, and our validation is going to be this evaluation and our training. So we're going to do this. Val data root. This is going to be data root. We're going to do a little F string here. And then we're going to say evaluation. And we're going to say train. That is correct. Okay. The EDU dataset is sharded. So you see here how this is already in shards. The sharding is kind of overkill for what we're doing here, so I'm probably just gonna get rid of this. No shards, blah, 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 crap. Okay, we don't need any of this crap. If master process, this is the distributed stuff. Let's just get rid of this. And if we actually look at the data loader here, here's your shuffle. You do need that. Let's see what else we can get rid of here. We can also do this. Reset next batch. We probably want length as well. Current shard equals 0. Tokens equals load tokens. Current position equals batch times self.t. This is all just sharding crap. I don't think we need any of this. What is he doing? I'm coding. Easier if we just point to a shortcut in that folder and enable GPT to browse it. There's no GPT in the loop here. This is just like all hard-coded. Are you trying to keep the same config layer and heads or match the parameter count? So he's asking a question on this model, right? Where we kind of arbitrarily picked this here, Mamba D model 768. What we can do is you can look at papers. So for example, what did they do here, right? So we can go here to this paper and they tell you the specific size. So hidden dimension of 4096, 56 layers, and the state dimension for each Mamba layer is set to 128. So what do we have? We have state dimension of 64, so kind of half of that. This is probably the D model, which is 4096. Right? Which is definitely more than us, but this is a smaller model. So I feel like matching this one probably makes sense. I don't know. Like I said, I'm not trying to like beat the current state of the art, but generally it's like if you just make these numbers bigger, it's going to perform better, but the GPU that you need is going to be bigger because when you increase these things, the total amount of memory it's going to take is larger. It's going to be longer to train, more annoying to train. So really, in fact, we should probably just reduce all of these, right? So actually, what is the sequence length that we need for this arc challenge, right? Like, what is the task length for this? Like, one task is how many different things? Jesus Christ, I probably should have looked at this arc challenge before I started doing any of this. Evaluation, let's look at this. Train, input, output. Damn, if only I could count fast. Why don't we should probably just load this. All right. Let's do our data loader, and then we'll step into it and load the data sets. If split equals train, we want JSON dot load. We probably want to do an OS lister. Let's see if we can get GPT to do this for us, actually. So we're going to copy the description here. We're going to do this. Data directory, copy. We're going to go here into GPT. We're going to do a new one. Can you write me a PyTorch data loader that loads batches of the arc challenge? Here is the description of the data set. And we also want to say, we also want to give it, let's give it this. Copy. I'm going to go here. Say, this is what I have so far. Make sure the quargs of the data loader match. All right, we're going to let it do its thing. Okay, data directory split. Here's the for OF splitter, data files, load data. It has a data set and then a data loader object. It's kind of annoying. Okay, I think we can do that. Let's copy this. Put it here. Boom. We're also going to need to import down here, probably, from torch.utils.data import data set data loader. Okay. Let's get rid of this load tokens. We're going to also need JSON. All right, so now it's all clear. Data dir train. I don't like this list comprehension. This is just no bueno. We can do this. Make this not a list comprehension. Okay. OS lister data dir, that's fine. F ends with JSON. Okay, that's fine. All of these are JSONs. File path equals blah blah blah. Okay. Self.datafiles.append. Okay, so now it's just creating a list of all these files. And then it calls this load data. Load data goes into this data file. It loads each individual task, so it's going to go into this and then load it. Is this already split into train and test? Oh shit. Okay, never mind. We had this wrong. So each task has a train and a test. Dude, what the fuck? Okay, so this is the quote-unquote train, which is the demonstration, which is going to be the input, and then the output is going to be this. Okay, I see what we're talking about here. Okay. For pair in task, train if self-split. This is incorrect, because right here it's thinking that, okay, we're going to be training and then evaluating on the test, but the way this is basically done is you basically have the X and then the Y. Self.x, self.y. So it's more like the input and then the target, right? So the target is what you want the net to output, which in this case is going to be this, right? And then the input is going to be this. So all of this goes into your network, and then this goes out. We're just going to be putting it all in the context. We're going to have to rewrite this. Task train test. We're going to want to create, like, put all of these in there. So really we're going to want to create these kind of like almost like tuples. This isn't great because here the problem with this is we're going to be basically putting this entire data set into CPU memory. This is kind of the way this is written right now. But I think this is small enough that it doesn't matter, right? The real way to do this would basically to be loading these. So like each one of these is kind of a batch. So you shuffle the files and then you pull each one individually, just so you don't have to have all of this in memory, which I think is probably what we want to do. So actually we're gonna ignore this. We're gonna do, we might want to get rid of that. We're going to come back to that. Length of self.data, that's fine. Get item, self.data IDX, I think that's fine. The data loader is where we're going to want to do our stuff, and already GPT fucked it up. We need to tell it to do what it was doing here before, just to copy the format. So where is the data loader that Karpamambathy had? It's up here, right? Yeah, here you go. BT process rank, num processes, like that. Okay, let's copy that. Arc dataset, this is the loader. So let's do it here. Okay, we don't need batch size, we don't need time steps. Get rid of that, get rid of that. Data root, arc AGI data. Training if split equals train, else evaluation. It's fine. Arc dataset, here it's creating the dataset. We don't need this split here, so we can get rid of that. And we can get rid of this. So now we're just creating an arc dataset object out of that, and then we're creating a data loader object out of that. This is, what the fuck? I wanted to subclass data loader, not create a weird data loader. Right, ideally you would want this to inherit from this, but whatever. The shuffle equals true is nice. This is going to be B, right? Matching this. Dataset, dataset. Okay. And also, this is incorrect as well, right? Because what we really want is shuffle should depend on whether this is evaluation or training. So if shuffle equals split equals train. So basically, if we're training, we want to shuffle the data set. If we're in evaluation mode, we don't want to shuffle the data set. What are people talking about? In the style of Karpamambathy, rewrite this code. I don't know if Karpamambathy's style is always like this. So, I mean, if you look at his other repos, I wonder if he always has this style. Like, if we just go to Karpamambathy And then we go to his repos. Let's go to like some other random Python repo. What about min-GPT? Let's look at this. Demo, min-GPT, model.py. Let's see. It's a very similar style. Yeah, he kind of is consistent with this style. I'm just looking at the comments. There's no typing. He likes this OO kind of. People who write PyTorch like really like this kind of object oriented where you're like defining the model as these objects rather than kind of the more functional JAX designs that you see sometimes. Okay. Let's go back here though. We want to try to get this working. Shuffle equals split equals train. Let's actually, we don't even need to store this as a separate variable. We can just come here and do this, right? We could, I also don't like this, like these kind of really long, kind of like weird fucking things like that. Just say if split equals train, do that, else. Like that. I just feel like that's cleaner, you know? And then we can also do like a little print here. Okay. Data loader. Now, next batch. Next data loader.iter. Stop iteration, data loader, iter, data loader. Next data loader, iter, inputs in item in batch. Okay, so we're actually going to have to data loader, iter, data loader, return. What the fuck is this, dude? Such a weird design here, but right, the problem here is that this batch that is coming out of this data loader, these are just JSONs. So we need to open these and turn them into actual like NumPy so that we can feed it into Torch. Let's do this. Let's go here. Do we want to try GPT for this? I feel like GPT is just going to like lead us down a rabbit hole. This is going to be more confusing. Decisions. Did he come from a C and C++ background? No, I think or maybe, I don't know, like he does have, if you look at his repos, like he does have C repos on here, right? He even has CUDA, notebook, C, HTML, Python, CSS, Lua, so like he writes all kinds of weird things. HTML. Let's put some breakpoints here. Let's go here. Put a breakpoint there. Put a breakpoint here. Hella swag, eval. We don't need any of that. We're going to be here. Torch.compile. And then once we actually load a batch here, you see, here's where we're actually going to load the batch. Let's put a breakpoint there. And then in the actual training, actually we don't even need it yet because we're going to hit that one first. Let's also make this a little bit smaller just so it doesn't take fucking forever. So we're going to come here. Let's make this 128. 128. Let's do 4. Let's do 6. Let's keep that 1024. Okay, so we're just making the model a little bit smaller just so we can debug a little bit easier. We're going to hit Control-Shift-1, and hopefully we hit our breakpoints. So there's our first breakpoint, right? So that means that, where did it go? Boom, 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 boom. Step.time, valloader.reset. Okay, so there's some other breakpoint that it got to before that because it went straight to this one. Okay, so if we go to task, here's our train and our test. So this is the one of these files, right? And you can also come here into this little debug console, and there you go. There's the actual file that it picked. Okay, inside that file you have the task train, right? So task train. There's your input, output, input, output, input, output. So really you want to iterate through this. You want to say for subtask, or I guess example is probably the better way to say. What is the actual terminology that Chalet uses? You will enter a test space. Is it symbol controls, answer validation, 400 tasks, and then each task has a bunch of inputs and outputs. Demonstration, test. Let's do that. For demonstration in task train, you know, if you use something like this, right, you want to use the same terminology and nouns that they're using for that, because if you use something like example, right, you start making your own terminology for this, it makes it harder for someone to come in and actually understand what the fuck is going on here. So just try to use the same names that they use. Demonstration input, demonstration output. How do we actually want to do this? Because it's basically like, do we want to load all of it? So this is the demonstration input, demonstration output. So when we're loading this into our model, right, it needs to be a sequence of things. So we're going to be going through this entire sequence of things. And do we put all of this into the context? And then this is the target. So this is all input. This is all the output. So actually, we kind of almost want to flatten all of this, right? If we look at our task train, and we look at the length of that, it's 3. So there's 3 examples. That matches what we have here, right? And then if we go length of task train 0, it's 2 because there's an input and output. And if we do length of task train 0 input, 30. So that means that there's 30. What is this? 4 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4 by 10, that should be 40. So where's this 30 coming from? Length of task. First of all, what does this look like? Ah, okay, so it's already 2D dot shape. It's not, it's a NumPy. It's a Python. It's 30 rows of 30. 30 rows of 30. You see how this is also in int? It's like a uint 8. 8 possible values. Okay. So now we need to think about the way that the scan works. We need to turn this into a sequence. How are we going to turn this into a sequence? Generally, when you have these Mamba models, you kind of just read them like this. But we want to basically, we probably want to read like this, like this, like this, like this, like kind of the whole row. And then we give it this one. Right? So let's do that. Can I ask a question? As far as I know, you're not working full-time anywhere. Is this enough money? Is the money you earn on YouTube enough to survive? No. I do work for people. And no, the money I make on this YouTube is effectively negligible. Because I also don't like monetize at all. You know, so I've had people offer me like some money to like promote some bullshit like machine learning products. But I don't want to do that. You know, like the point of this YouTube is not to make money, and I don't want to be promoting some shit product. I also don't add ads, right? So like YouTube is complaining right now. It's telling me, hey, now would be a good time to insert ads, right? So like they're trying to encourage me to insert these ads halfway through the stream, but I don't want to do that either, right? Because I don't want to be forcing you guys to look at ads. So I am not trying to monetize this YouTube channel at all, right? I try to run as little ads as possible. And I also don't want to promote like weird shit products. So yeah, this YouTube channel is really just for fun. Leave space holders. Don't do it all at once. Scan, you can get placeholders automatically by copying it from examples. Based on this, I quit my job. I don't know if you want to quit your job. Okay, well, what happens if we just were to say this? Length of task train 0 input dot, we turn that into a numpy dot nd array, like that, unmatched, import numpy as np, list object cannot be interpreted as an integer. What? Type list. Pretty sure we should just be able to fucking turn that into an array. All right, there we go. np.array shape. Okay, there's our 30.30. So that's the input, and then what is the output? I'm kind of working in this little bottom corner, so it may be hard for you guys to see. Let me see if I can make this a little bit bigger for you guys. There you go. Maybe go like this. Is that better? All right. Input 30 by 30, output 30 by 30. Where is this fucking 30 by 30 coming from? Right? Like, the output should be half the size of the input. Why is that not the case? What about the test? Test output, test input. All of these are 30 by 30? What? What? Just input. Let's turn these into arrays here. And let's do the same thing for the output. I'm still confused. Why are these 30 by 30? Do you guys know that? What's going on there? Huh? What is going on there? Symbol colors. Let's look at this data set again. this is so bad. This is trash. Oh, these are slightly different lengths too. See how some of these are different lengths? Ah, okay. So it's just that these are different lengths, so it's not even the same. This is just a random example, but sometimes they're small, sometimes they're larger. See that? These have 3. Train input 3, 3, 3, 3, 3, and then you go, and some of these have more. Dude, so it's like variable length. That's not great. Okay, but anyways, for test case in task test, you have an input and output. This will be demo input. You have demo output. You have test case input. And you have test case output. Okay, so what is going to be our target and what is going to be our input? So what are we actually giving to the net, and then what are we actually telling the net to output? So what we are giving to the net is probably going to be this, this, and this. Right? It's going to be the demo input, demo output, and then test case input. So this is going to be demo input dot flatten and then np dot or hcat, I think it is, hstack, something like that. Let's see. We're going to basically want to concatenate these. I think it might be vstack, but we'll see. Output.flatten, test case input.flatten. Nope. And then we're going to do the target is going to be this. Okay. So basically we're going to give our net all of this, boom, 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 all flattened, boom, 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 boom. We should probably actually weave them. No, that's fine. And then we're also going to give it this. Boom, 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 boom. And then it's going to output this. Boom, 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 boom. I think that's what we want. Let's save this. Let's put a breakpoint again right here. Actually, maybe right here. So we're going to Control-Shift-2, Control-Save, Control-Shift-1. We're going to let it run again. It's going to break right here. Boom. Let's actually look at these. So what are demo input? Demo input is a 30 by 30. Demo output, also a 30 by 30. Test case input, 30 by 30. Test case output, 30 by 30. 900 total. Demo input, 900. Demo input.flatten. That should just become a 900 by 1. Yep, that's fine. Demo output.flatten. Also 900, and then test case input.flatten should be 900 as well. Okay. And then the test case output. Let's confirm that this works fine. I don't think this is 100% right. Let me double check that. Oh, np.hstack.shape. Yeah, that's what we want. Okay, so you see that? We've basically flattened everything into this 2700 context, which I think is beyond what our neural net even can support here. So we might have to increase this. Block size 1024. We're going to want 2700 plus 900. We're going to assume that this is the biggest one, right? Because we were looking at this and it seems like some of these are different. So my bet would be that he used the first one that you pick here is like 30 by 30 is going to be the maximum size. So let's just assume that that's the maximum size here. And let's pick a number that's kind of bigger than that. So 1024, let's do times 4. Can anybody do that in their head real quick? Too slow, 4096. Which normally would explode the amount of memory that we need, right? Because transformers are quadratic with respect to the sequence length. So if we just 4x'd our sequence length, we would basically be 4 squared 16xing our total compute. But we also reduced the size of our model, so our model is smaller, and we're also using a hybrid architecture which has these Mambas in there, and these Mamba blocks are linear with respect to this size. So we should be more flexible here, and I feel like we should be able to do that. Okay. We're here, up here, boom, boom, boom. No, we're down here. So now we've created this kind of supervised learning X and Y target. And if we go, we eventually create our data. Let's put a breakpoint right there. Then we just Control-Shift-1. Let's get rid of this breakpoint. Okay, now we've gone to here. So now our data is a list. Length of data is 400. So each task, right, because this is reading one data, or one JSON, is going to be 400 demonstrations. And then each of those demonstrations, data 0, let's say this is going to be a tuple, right? So let's say the first one is going to be the input, which is going to now be a NumPy array, and then the output is going to be that. My mutilation of programs is not viable. What do you mean? You can write code in debug? No, you can't. So like when I'm writing, it's like the program is frozen right now, right? So like if you change any of this, like you're gonna have to kill it and then run it again. But like I'm keeping track of in my head of like when I ran this and what changed since then. But now we have basically a list of these with inputs and outputs in NumPy arrays. We do need to kind of normalize these, right? But I think that's where the tokenizer is going to come in. So there's some logic here with the tokenizer. We can actually look at what Karpamambathy was doing here. So self.tokens equals load tokens. Where's this actual? Okay, here it is. File name, s-type in32, torch.tensorMPT long, ptt. Load tokens, self-current position, return xy. You see how he's doing this as well? X, Y, view BT inputs and BT targets, and then ultimately he has this next batch function which returns an X and a Y. So we're going to want to do that as well. So in our return next batch, you see here they're calling it input and output. So we can just call it X and Y, which is kind of what we were calling it before, or in our thing up there anyways. Next, data loader iter stack for item in batch. That's probably fine. Let's do that. Control-Shift-2, get rid of that. Now we're gonna go in here. So let's see if we can hit this breakpoint. Going to hit this one. Nope. Valloader.reset. Arc data loader has no attribute reset. Okay, so Arc data loader needs a reset function, or we can just get rid of that. Let's do this. Reset. Nope. Reset. Self. do that. Rerun. Wait for it. Boom. All right, there we go. Val-data-loader.next batch. Okay, let's get rid of that. We're going to breakpoint. Arc data loader has no attribute data loader iter. So the problem here is that this like PyTorch or GPT gave us this like weird fucking like data set wrapped by a data loader kind of thing. But I think it's like we don't really want to do this. We could probably just get rid of all of this crap here and just do this. Move this like this. We're just going to have these explicitly here. Like that. Oh shit. I'm fucking with that. I don't want to do that. Okay. And then we're not going to need this. We can basically just say train data loader or train loader equals data loader like that. That's what we want. And then we can get rid of this fucking weird crap right here. Oh, but then we're going to get, you see the problem here is then we're going to lose this process rank num process split. So we're going to lose the distributed stuff, but I don't think we're going to need that right now. So let's get rid of that. All right, so now we only have this data set here. Loading the data, boom. We're going to have to figure out how to basically normalize these or turn them into something that we can properly consume. That should be fine though. Let's put a breakpoint here. And let's run this, make sure it runs. Hupo, I'm really interested in SLAM for robotics. Any resources you would suggest for beginners? There's a lot of different types of SLAM, and it's also like starting to change. So I've done a stream on this one before. So this is like a type of, it's not really SLAM, but it's like a type of reconstruction, which I think is within the SLAM umbrella. Honestly, if you're just getting started, like, look at the like ROS SLAM. Right, so like the robot operating system. This is like the open source robotics toolkits. Like they have some SLAMs. I don't know if this is the good one. I haven't used ROS in a while, but like if you're just getting started in robotics, like use ROS and use the SLAM that's in there. If you want to get straight into coding, if you want to just go into reading SLAM, simultaneous localization and mapping, there's probably like relatively recent papers that you could read. Understanding SLAM in autonomous vehicles, yeah, like maybe read something like this. But even this is kind of old because I think the problem is like a lot of these SLAM techniques are like based on old computer vision techniques. And I think that you're starting to see a lot of this get rewritten with modern architectures. So I don't know, it's just like not necessarily a good place. Definitive guide to mobile mapping. What the fuck is this guy? Like what? Decline all cookie. Like look at this dude. He's balling. He's out of control. Someone needs to stop him. Okay, so these guys are trying to sell you their bullshit product. I don't know. You can also do SLAM with like Sonar Arduino. Ultrasonic SLAM. Here you go. Boom. This might be useful. So a lot of like first robotics projects that people start with are these little ultrasound sensors. So if you've ever seen like one of those little starter robotics kits and they have these little things, right? These are basically like a little bat. Bats are basically screaming and then they're listening to their sound when it comes back. This is the same technology, right? You're sending out a little blast of ultrasound and then you're listening to when it comes back. And what this does is it gives you kind of a distance of your little robot to like the nearest point, and you can get that little point. And that's probably the simplest type of kind of visual sensing. And if you combine this type of visual sensing with a very simple kind of like wheel odometry and stuff like that, you can start doing SLAM with a very simple robot and very simple sensors. So if you're just getting started, I would maybe recommend that, but I don't know. That's all I got. All right. Where were we? Return data. Okay, we were here. This is our data. Actually, you can see, look at the different lengths here. See how some of these are short, some of these are small, some of these are long. Let's see what happens if we just keep running that. Where does it break? No, no. Let's just comment this out. Val loader.next batch. I think you just need to do this. Because this is no longer Karpamambathy's weird data loader. It's like we're using the PyTorch data loader. I think if we do this, data loader is not an iterator. You kidding me? Pin memory sampler, drop last, batch sampler, like this. How to use PyTorch data loader. Okay, so here you see they're making a data set, and then they're going to wrap that in a data loader. Okay, that's cute, but where's the data loader? Here we go. Preparing with data loaders. Okay, so you have the data set with a batch size and then shuffle. Okay, technically you don't want to shuffle on test, but we'll let them do that. And then you need to wrap it with an iter and then do next. Okay, so we're gonna need to do that. We're gonna need to say train loader equals iter, train loader, and val loader equals iter, val loader. And those will turn it into an iterator, which means that you'll be able to call this next function on it like that, right? So let's control 2, control 1, run it again. Let's put a breakpoint right there. Expects each tensor to be equal size, but got 2700 at entry 0 and 2200 at entry 1. Okay, so this is the problem, is that these are not the same size, right? We've been kind of like snooping on this error the entire time. So really what we need to do is we need to pad these so that they're all the same size. So we can actually probably get GPT to do that. Let's try to get GPT to do that. So let's copy that, come here, new, paste. We're going to say, I need to pad the inputs and outputs for my data loader. Come here. We're going to copy paste the data loader that we have, this one here. And we're also going to copy paste this part here just so you want to give PyTorch or GPT like all the different parts, because if you don't give it, then it starts imagining it. All right. So you see how now it's added this extra stuff here, max input length, max output length. So we're going to pad our inputs and our outputs. So now you need to have this config variable of like, okay, well, what are you going to pad to? All right, so you see it's basically largely the same, and then here you go. It's adding these pad sequence here. So let's add that. Pad sequence, NP zeros, min, length, padded, okay. Cool story. Let's copy this. Another tip I like to do here is we're going to Control-Shift-2. We're going to just commit this. So the reason I want to commit this is like we're going to say progress on data loader. And we're going to commit that. So I'm going to paste this in here. And sometimes when you copy paste things from GPT, it starts changing other things that you didn't want changed. So now when I paste this in, right, I'm going to be able to see what it changed, right? So I can look at these lines here and say, okay, what did it actually change? So it changed this. And what did it do? It got rid of that and changed it to that. That's fine. Just kind of shifted it. And here it added these two lines. That's fine. I wanted that. It added this here, max input length and max output length. We probably want these somewhere that's not that. So like, where did Karpamambathy do that? So he has a config object here. So maybe let's copy that style. Let's do the same kind of thing. Let's make a little data class. Let's do arc dataset config, and let's do that. And then we'll create a new arc dataset config object when we want our data. Where is it? Right here. So we'll say dataset config equals arc dataset config, and then we'll feed that into here. And then we'll go into our arc dataset, and this will now, rather than receiving this shit here like this, which is a little bit sloppy, we'll just do this, config. And then we'll have to come down here and then do this. Okay, so now we kind of copied the Karpamambathy style of having these like data class config objects like he had here for the model. And then we basically just made one of these for our data set, and that's where we're going to store these, which this max input, max output. We should probably have this not be that. Let's do something a little bit nicer. Let's do 1024 by 3. Something like that. That seems kind of gross. Okay, whatever. Fuck it. Let's do that. You see how it added this as well? So it's changing these to float 32s. That's not really what we want to do. This is still wrong, right? Because it's like technically this is like a discrete space. There's like only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible values there. Okay. Let's see if it runs though. It's already 11. Fuck, dude. This is already way too long. What is a pad? A pad is when you're padding here, padding tensors. Let me see if I can find a good picture of this. Yeah, something like this. This is a good example. So you have these tensors, right? So our data is kind of like this, right? Oh, open image in new tab. Open image in new tab. Like this. Jesus Christ. So I guess you guys can see this, but our data is not the same size, right? Each of these examples, some of these examples are 2,700 long and some of these examples are 200 long, right? That's what PyTorch was complaining, right? You see that? Entry 0, which is the first example that it pulled, 2,700 was the input length. The second example that it pulled, 222 was the input length. So these, I guess here they're calling it ragged tensors, an example on ragged tensors. So like they're not all the same size, but when you're going to be feeding this data as a batch, right? Because we're going to be training this in batches, the batch size needs to be the same. So we basically need to pad all of them so that they're the same size, right? So that's what the padding is. Yeah, filling it with the empty space, specifically zeros. So we're filling it up with a bunch of zeros. Yeah. Did this train? Like, what happened here? What? Why did this do nothing? Positional argument follows a keyword argument, syntax error. Okay, line 416. Oh, okay, I think when we put this config 416. Yeah, okay, so you see this needs to be different here. This is a Quarg, it should be just like that. And actually the cleaner thing here would just be to do this, and then we'll have a config.datadir, and then we'll have a datadir like that. And then when we go down to the use of this, we'll do this. Okay, so now we've basically put the datadir inside the config. Okay. Here's our x. See, if we look at the size of this now, x.shape, it's a 16 by 3072. Okay, so the 16 is the batch size. So now we have a batch of 3072 length, which is basically all of this shit flattened. And kind of like, really this is not ideal at all, right? I feel like if we really wanted to kind of do this correctly, we need to spend more time thinking about what is the correct way to do this, right? Because a different way to do this would be to like think of this like a language model and then kind of put in kind of like a input, like literally writing the word input and then giving it this, and then literally writing the word output and giving it this, and then literally writing the word input and giving it this, and then literally writing the word output and giving it that, right? And the advantage of doing that is not even, the advantage of doing that is that you could probably then, rather than training something from scratch, which is kind of what we're doing here, we would be able to take something like this Samba, which is someone who trained a Mamba, another hybrid Mamba, specifically for on Slim Pajama and stuff like that. We would be able to take this and then effectively fine tune it on this type of data, right? So that would give you all the pre-training intelligence that you get from this data set, whatever they're using. What is the actual data set here? Blah, 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 blah. The Phi 3 Mini. Oh no, outperforming Phi 3 Mini. Where is it? What is the data set? Code review, one can easily train. Pre-training. Slim pajama. Okay, I literally just said that. Okay, so you could there's some intelligence in this slim pajama that's going to help you on this task, right? Like if you take a transformer or if you take this hybrid Mamba pre-trained on slim pajama 627B and then fine-tune it on a text version of this task, it's going to perform better than what we're doing right here, right? What we're doing right here is we're training it from scratch only on this task. So it's going to be extremely overfit to this data set. But if we're just sitting here doing this locally, it's going to be way easier to just train from scratch with a little tiny version of the model, right? Because we reduce the size of the model rather than pre-training and then fine-tuning, right? If we were pre-training and then fine-tuning this, it would be kind of a completely different repo, right? Because then you wouldn't really necessarily need to make a new data loader for this. It'd be just taking this ARC challenge data set and turning it into a language model data set, right? Where you have, it's basically very similar to like an RLHF where you'd have like an input, output, and you're like literally writing like user assistant, user assistant, user assistant, right? But in this case, it would be like demonstration 1, demonstration 2, demonstration 1, demonstration 2, and then you would be like demonstration 1, demonstration, and then it would give you the output. That would probably be the best way to do this if you wanted to really push the state of the art. But right here, we're just kind of fucking around, right? Like we're just kind of sitting here, kind of playing with this stuff to try to get a feel, right? We're trying to like live in Karpathy's code and kind of like do stuff his way so that we can kind of live out our fantasy of being Karpathy. Chalet is making it difficult for no apparent reason. Yes, Chalet seems like the guy who just makes things difficult because he can. You know, he loves being a contrarian. If you have an opinion, he'll just take the other opinion just to be the opposite side of it. Okay. All right, but another thing here, so you see what happened is that this x dot device, it's on the CPU. So right now, this batch is living in our CPU memory, so you can actually see it here, right? 14 gigabytes. When we move it to the device, we should see it appear in our GPU memory. So this is a kind of a really tiny batch, so it's going to be hard to tell. But why don't we do that? Why don't we do this? Put a breakpoint here. Come up here. Make this like something much bigger. Let's do 128. Even 128 is going to be pretty small on this. Let's do 256. Because this is now a very tiny little data set. All right, let's run it. So we're kind of hovering around 2 gigs. Now we hit the next, right? We can look here. I don't think you guys can actually even read that, but we go boom. It barely changed, but we're at 2.3, and now if we hit boom again, 2.4, so that's actually kind of tiny. We could probably use a much, much bigger data set for this. And why is it so much smaller than the text data set? Because when you're doing a text data set, right, even though the sequence length here, it's 1024, but it's 1024 tokens, and each of those tokens has some, it's basically like a vector, right? So it's 1024 vectors, but in this case, it's just 1024 just numbers, right? So actually, we probably want, let's do this. Ooh. Ooh. Let's come here. I want to turn, or the values in each of the examples for my data set are not torch floats. They are indices of 8 possible values representing 8 possible colors on on a two-dimensional grid. For example, and then we're going to give it one of the examples. So we're going to go here. Let's copy one of these little ones. Let's Control Z. Let's do this one. Input. Oh my God. Let's Control 6. Let's try one that's not like indented terribly. Maybe this first one. This first one seemed fine. Right here. This one here. This one's nice and tiny. Okay. Output, input. Like that. Okay. Copy. I want you to turn these into one-hot vectors. That's kind of a generic thing to use. Okay. Pad and one hot encode, is that even real? Did it just hallucinate that? So 2017. Oh my God, dude, this is so crusty. No. Let's see, data set. Why doesn't he give us a data loader, dude? Why don't you do that? Why don't you do that? Jesus Christ. All right, guys, I got like 15 more minutes. Let me go back. Where was this GPT? Right here? Let's copy this. This is not even the right thing, though. Whatever. We'll just leave it like this. I think that's fine. You know what? It's okay. It's okay. Perturbing the data can help with generalization. Yes, what you're referring to is called data augmentation. So in data augmentation, you're basically adding noise to the data, right? So like data augmentation is task specific. So in this case, what type of data augmentation could we add that would work with this task? It's actually kind of difficult because this task is very fragile, right? Like in images, data augmentation is actually quite easy, right? Because intuitively you can be like, okay, well, if I want this to be classified as a cat, like flipping it upside down, it's still a cat. Rotating it is still a cat. Stretching it is still a cat. Grayscale, it's still a cat, right? Like there's so many different transformations that you can apply to an image that give you an extra little data point to train on, right? But unfortunately for this, I don't know if there's much data augmentation you could do. Maybe flipping it, right? I wonder if you vertically flip this randomly, it probably still counts. And maybe you could flip it the other way too, right? So you could, I don't exactly know. I'd have to like look a little bit deeper into this data set, but perhaps horizontal and vertical flipping, that type of symmetry would ensure that the example is still valid. But if you started randomly changing some of these little grids with other little colors, it probably wouldn't work super well. So I don't know. That would be my guess if I had to come up with some kind of augmentation for this. Am I filling up the empty space? Yes. Okay, so the problem right now, though, is that this isn't even the same size. So actually, if you remember right here, we're at 16. See, it's 256 by 1024 because we made our batch size 256. Let's make our batch size smaller again, just so we can load the text. If we Control-Shift-2 to kill the debug, and then we go back to the original data loaders, so we do this, boom, and we do this, boom. We're also going to need to uncomment this part that we commented out. And now we run it. We're going to also breakpoint right here. And I mean, we changed this as well. Control-Shift-2, let's do this. X, Y equals valloader.next batch. Let's run it. Okay, so now we're waiting. It's going to break right there. Okay, so now, actually, if you look at the shape of this, 16 by 1024. Ah, okay, so that actually works because the... Actually, that's very convenient because it basically means that we don't need to do this one hot that I wanted to do because it's already in that form. Right, let's actually inspect one of these. So let's do X 1 or 0 all. What are the values here? You see that? So this is already dot shape dot type, sorry. Type. It's a long tensor of integers. So you see this, I thought it would already be in embedding form, but it's not, right? So basically what this tensor is, it's 16 batches, or a batch of 16, where each element in the batch is a tensor of length 1024, and each index in that 1024 tensor is basically the ID of the token. So this is saying token number 50,000, token number 464, token number 13362, token number 3974. So that's actually basically the exact format that we have in our data loader, right? Our data loader is also doing that. Let's come up here. It's just that this, we don't even need this many. Now we just need whatever it is. I think it's like 8. So let's do that. 8. Come down here. It was a torch.long, so let's copy that right here. Long tensor. Like that. I also don't like how long this line is, so like I'm gonna do this. Like that. Oh. This is what I'm talking about. You see how like I just spent like 5 seconds there doing something that literally has 0 functional value? It's just that like that's the problem with like being too opinionated about style, is that you just waste a bunch of time doing a bunch of crap like that. Okay, let's come back down here. Let's put these back in there. And let's run this. This doesn't need to be an F string. Let's comment this again. Let's comment that, put that there. Okay, I think we should just be able to run this and we should be able to get past that. Let's see if we can get to the eval here. Ooh. Make sure total batch size is divisible by DDP worlds. Oh, okay, so this is the distributed training. It wants to be able to debat. This is not the right thing. We didn't change the right thing here. This is wrong. Total batch size. Undo. What I want to change is the vocab size, which I think is part of the model config. So up here in the model config, vocab size, this is going to be our 8, right? That's how many there is. Let me double check. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So really there's 10. And we would want to add kind of more special tokens there. That's probably the better way to do it, but God. So you need this. Which means that I probably don't need this. Gotta love this kind of circular bullshit logic. Long tensor y. Okay. Oh, nope. Syntax error. Run it again. Causal conv with last channel layout requires stride 0 and x stride 2 to be multiples of 8. BSD to BDS. Okay, so now this is within the Mamba block. So the Mamba block does not like this weird setup that we have where we have a low vocabulary size. So let's think more about this. Stride to be multiples of 8. So we look at the Mamba. Let's actually look at the Mamba 2. So we go to our train. Then let's go into the part where we're actually making these blocks right here. You have your model, your state, your conv, head dim, DT max, bias, chunk size. One of these needs to change. Let's go back to the actual error, see what was going on. Causal conv1d in forward. Let's go to this actual file. Conv1d rearrange. Ooh, the problem is that that's inside the thing, so we don't really know where this 8 is coming from. You know, maybe we don't actually need to change the vocab size. We're just going to have a bunch of empty vocabulary, but that's probably totally fine, right? Let's go back to our train. What happens if we just do what it used to be right here? Undo. Run. Run it. No, still the same error. Okay, so it wasn't because of that. Generally, I was stride to be the multiples of 8. What is that empty space being filled up with? Noise? No, it's being filled up with zeros. So technically just more of these black squares, which are the 0. If this just, let me see if I comment out the Mambas. Does this run? So if we just do this, and run it, this is no Mamba blocks. No, you see it's also complaining, so it's definitely the data. Expected input batch size to match target batch size. Ooh, this is a big error. So basically, for the layer norm BT vocab size, is this even the right size? 16 by 3072 by 50304. Okay, but then what is the targets? Where are the targets? Targets. 16 by 1024. Okay, so you see this is the problem. This target, forward, blah, 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 also needs to be the same size, right? You're doing this cross entropy loss and you're basically using the wrong sizes here. Why does this work with text though? Right? Because really all we did was just give it a batch of effectively tokens. We're keeping the vocabulary size the same. It's just kind of weird because it's it's only using the first like 10 tokens, but like I shouldn't have to modify this code is kind of what I'm getting to. IDX 16 by 3072. Position embeddings, token embeddings. Targets.shape, x.shape. You're feeding your X through all your blocks. Then you have the very last layer that turns it into this. Your logits or logits, as Karpamambathy calls it. Logits.shape. Okay, so now the last layer is just 128 neurons, right? And then you want to turn it into these logits, which are basically telling you what is the probability that each token in this sequence is one of these 50,000 possible vocabulary tokens, right? So if you look at, for example, logits of batch 0, or element 0 in the batch, so 0 out of 16, and then the first element in that sequence, you see that? You see these numbers. So basically what this is saying is that much higher probability that it's token number 2 than it's token number 1. Okay. But really, the targets should be telling you which token is it. What is the actual token that you wanted this to be? I think maybe we need to do targets is not none. Can we do this? If we look at the targets, right? Targets, let's do the 0th, so the first element in the batch, and then the very first one in that sequence. You see that? So it is kind of in that IDX mode. We need to turn this into a one hot. Let's see if GPT can redeem itself. We're close, guys. I know I'm technically over time here, but I think I'm going to go PyTorch turn a B by L target into one hots. Okay, is this a real one? Is this even fucking real? Torch.nn.functional.oneHot. Let's see if we put targets in there. There you go. That's kind of what we want. But you see how it's only 10? We actually want one hot targets, and then we want the number of classes. Oh my God. I can't see. Num classes, we want that to be the vocab size. Which in this case is like whatever, 50 million, 50,000. So we should actually probably pull that out. So here where we define the model, right here, you see we should probably do this, model config equals, pull that there, and then do model config, which allows us to then take this and then come down here where we're running into this error, where we were here. Where's this bug? Right here. Then we can say targets equals targets, or torch.nn.functional.oneHot targets, and then num classes equals self dot, or no, model config dot vocab size. I don't think we need that float. All right, let's see if that works. Model config is not defined. Let's run it again. Okay. Let's double check. Logits.shape, targets.shape. That's correct. What is going on here? Logits.size -1, logits.view -1. What does this give you? And then what do we have? Okay, I know what's going on. No, okay, so the problem here is that the way that this cross entropy loss works is it's basically predicting the next token for all of them, right? That's not what we want to do. So what we want is the output to be the same length as the target, right? It's like we're more like saying, we're more kind of treating this like a supervised learning problem, right? Where you have like input this, output this. But really, the way this training script works is it's a language model training script. So really it's more saying, okay, if you have this, output this. If you have this, output this. So it's like it's creating this cross entropy loss over the entire thing over next token. So the way to actually solve this is not to do this fucking shit I was trying here to do it with this one hot. We're gonna kill this. It's basically to do this. Come up here into the configure optimizers, into the data loader here, and not do this X, Y. It's going to be basically, we're going to actually add max test case output.flatten here as well. We're going to basically put all of it, this big brick, into it, and then get it to predict the next one. So then Y is going to basically be that, but shifted by 1. Shift by 1 for next token prediction. I don't want to do that. I want to do like X one to the end plus pad. Padded sequence. Where's the padded sequence being called? Did we accidentally get rid of the padding? Where the fuck? I thought we were doing padding. I think we accidentally got rid of the padding somewhere. What? All right, let's go to our thing here. What changed? This is fine. That's fine. Okay, I think this is fine. Let's try it. We need to add like one more in there. Let's add a 0. All right, let's run this. Expects the tensor to be of equal size, but got 3600 entry 0 and 230. Yeah, this is like the padding, which we somehow lost. I don't know what happened. And max input length and max output length are actually going to be the same. So let's do max sequence length. We'll have this be the 4096. We should probably just have that be the same thing as the version of that in the model config. All right, let's run it again. Didn't pad it. Now we move that down. CUDA out of memory error. Okay, we need to make a smaller batch size here. Let's also put these Mambas back in. Right here. Hybrid architecture engaged. And let's also make the batch size smaller. Let's do 2. And now that we know we didn't have an error with the vocab size, let's change the vocab size back to 10. Okay. Oh my god, dude. What did we try? 16. Come on, dude. Come on. Okay, so we didn't actually solve that problem with the Mambas. We're going to have to figure that out later. See, this is always such an issue, dude. This is why we can't have nice things. Okay, boom. That did it. I mean, this hella swag eval is going to be complete nonsense. So we can probably take that out. Could probably take out this generate. Yeah, let's take out the generate and the hella swag eval. If we can get it to just do one training batch here, I think we can call it a day. Oh, we still got the same issue with this trainer batch. So let's comment that and do train loader next, right? Because we already turned it into an iterable. See how much memory it's taking up right now? It's about 9 gigs of memory on our VRAM. Stop iteration has occurred. Okay, so ARC dataset, load data. I think we need to add like a repeat. I think there's a way to do that here. ARC dataset, repeat or something like that. I'm pretty sure you can do that, but dataset PyTorch. Give me the dataset object. Dataset PyTorch API. Datasets. Source. Sampler class index. Because it ran out. So the problem is that this training loop, you see how it basically just, it has some set amount of steps that it's going through. But this train data loader here eventually runs out of data. So like once it goes through all of the data in the train loader, it hits this stop iteration and it says, okay, I'm done. And sometimes you write your training script such that it's basically like kind of like this, you know, for X, Y in next train data loader. So the number of iterations is literally just fixed by this train loader. But the way that Karpamambathy wrote it here, has like some hard-coded number of steps. So you have to basically make sure that the train loader only has that exact amount of steps. All right, grad Akum steps. Where is he doing this? So we can just control. There it is. Total batch size divided by B times T. So the total batch size should just be the length of the data set. So we can actually probably do this. Total batch size equals length of train data set, which we don't have until after. So let's actually pull that up. You see these data sets here? We're going to move this up here. Right? So now the batch size is just going to be the size of the training data set, which is effectively just one epoch. And actually, we're going to have to move the data loader down here. So it's going to be like this. Okay, let's run this. Assert total batch size mod B times T times DDP world size equals 0. Make sure batch size. Okay, so the problem here is that this sequence, like, because we're padding shit, it's not perfect, right? So this should be model config, or actually should be dataset model config dot, and we don't even have the model config yet, so we should just do this. Train config, move that there, and then we'll have a test config. And then we'll do train config, and I'm pretty sure we added max sequence length there, so we're gonna basically come back here, and we're gonna say train config dot max sequence length. And this is also gonna be times train config dot max sequence length. About 8 gigs of memory right now. You can see our CPU is going crazy. What do we got here? Object has no attribute B. Okay, so the problem is that Karpamambathy's dataset loaders have a property called B. So you can see here, we don't have that. So the best way of doing this I don't want to necessarily mess with well, here's the thing. B and T are going to be the same no matter what, so I think we could just do that. Stop iteration. Come on, what is the microstep right now? 0. Train loader. All right. Here's the hacky way to fix this. So we're just gonna literally remake the train loader and then run it again. So this is extremely hacky, but basically we're saying, okay, if you're still stepping and you run out of this train loader, just fucking reinitialize, or no, from the train dataset, sorry. Train dataset. We're gonna have to call this something else. I think part of it is that we renamed it, and that's why it's like dying here. Train iter val iter, which means we need to change this one. Val iter. And then we need to come down here. And this needs to be train iter. And this needs to be train loader. And this here, train iter. No, this is wrong. This needs to be like this. We're close. Almost there. If we can only just get this to just train. All right, there we go. It's training. Look at that. Oh, shit. Dude, we did it. 100% GPU utilization, 350 watts, about 8 gigs of VRAM. Pretty good, team. All right. I think I'm just going to end it there. I know there's like a million things we could do, and we didn't even really do anything, to be honest. Like, we just kind of did some shitty data loaders and messed around with some arc eval, but I got to end it there. I'm just going to say end of stream. Commit. Plus. Sync changes. Okay. I'll be back tomorrow. We'll probably just keep working on this repo, see what happens. You know, you're welcome to come join. Thanks to our Lord and Savior, Karpamambathy. But if not, have a great weekend. See you, everybody. Check with Mambas. We'll leave that for tomorrow. How about that? All right. See everybody later. Thanks, Raphael, Jigar, Luis, Godbuddy, Cheb Khaled, Julian, Aditya, Bob, Testin, Chicken P, Ed, Aries, Ajas, Tarun, Nawal, Tassadon, Eric, Zorg, Sayed, Sagar, Harsh, XXYYZZ, Zorg, I Like AI. Thanks everybody for hanging out today, and see you guys tomorrow.